There are visitors to our world that arrive in utter silence. They appear in the velvet darkness above, paint a fleeting luminous stroke across the stars, and then vanish again into the profound quiet from which they came. Halley's Comet is one such visitor, a silent traveler returning to our skies again and again across the whole of human history. Where does it go when it leaves us? Where is its true home? Tonight, we will wander through this question together, not in search of startling answers, but as a gentle exploration of a cosmic story. But first, allow yourself to settle in. Find a place where you feel completely at ease. Notice the gentle rise and fall of your own breath, a quiet rhythm in a quiet room. Let the day and all its concerns begin to soften at the edges. Before our journey begins, I would love to know where you are resting from tonight. If you feel inclined, you might share your city or town and the time of your evening in the comments below. Our story begins not in the cold, distant reaches of space, but right here, in the quiet humility of a darkened field or a silent city rooftop, with our gaze turned upward. It begins with the simple, timeless act of looking at the night sky. The stars, in their serene and predictable patterns, form a familiar map, a ceiling of quiet light that has comforted humanity for millennia. They are the constants, the fixed points of celestial light against which our world turns. But every now and then, a stranger appears among them. This stranger does not twinkle like a star, nor does it move with the steady, stately pace of a planet. It is a soft, ethereal smudge of light, a whisper made visible, and from it, a tail of incandescent dust and gas stretches away, like a brushstroke of smoke against the black canvas of the cosmos. This is Halley's Comet, a celestial wanderer that has haunted and mesmerized the human imagination for as long as we have been recording our history. To see it is to feel a profound connection to the past, a sense of shared experience that transcends centuries and cultures. The same faint glow that you might see once or twice in a lifetime was witnessed by your grandparents, and their grandparents before them, stretching back into a time when the world was a vastly different place. Ancient Chinese astronomers, Babylonian priests, medieval monks, all of them have stood under this same sky, looking up at this same silent apparition. It is a familiar stranger, an object that feels both intimately connected to our human story and yet profoundly alien in its nature. It is a reminder that the sky is not a static diorama, but a living, breathing space, with travelers passing through on journeys of immense and almost unimaginable scale. When you imagine this comet, do not think of it as a rock or a star. Think of it instead as a ghost. It is a spectre of the early solar system, a ball of ancient ice and dust that has remained largely unchanged for billions of years. It moves with a quiet grace, its path dictated by the invisible hand of gravity. Unlike a meteor, which flashes across the sky in a brilliant, momentary streak, the comet lingers. For weeks, even months, it can be seen hanging in the heavens, a patient and silent observer of our world. Its movement is slow, almost imperceptible from one night to the next, but it is moving, following a precise and predetermined path that brings it close to the warmth and light of our sun before casting it back out into the darkness. This journey is the heart of its story, a vast looping voyage that defines its very existence. It is a creature of two worlds, the bright, warm inner solar system, and the cold, dark, mysterious realm that lies far beyond our sight. And in that duality lies the gentle question that we will explore together tonight. What is this comet? And from what far country does it travel to grace our skies? We are not just looking at a celestial object. We are witnessing the return of a messenger from the deepest, most ancient parts of our own solar system. The universe, for all its seeming chaos, is a place of profound and reassuring rhythm. The earth turns, bringing the gentle cycle of day and night. The moon waxes and wanes, pulling on the tides with its silent gravitational breath. The seasons change, a slow and steady pulse that governs the life of our planet. And among these familiar rhythms, there is another, one that plays out on a much grander scale. It is the rhythm of Halley's Comet, a celestial beat that measures time not in days or months but in human lifetimes. Approximately every 76 years, the comet returns. This is not a random or haphazard appearance. It is a predictable, reliable event, as dependable as the turning of the Earth. Its orbital period has varied slightly over the centuries, sometimes a little shorter, sometimes a little longer, influenced by the gentle gravitational nudges of the giant planets it passes on its journey, but it has always come back. This constancy is one of the most serene and beautiful things about it. In a world of constant change, the comet is a touchstone, a celestial appointment kept across generations. The grandparents who pointed it out to their wide-eyed grandchildren in 1986 had heard stories of it from their own grandparents, who saw it in 1910. And so it goes, a golden thread of shared experience woven through the tapestry of human history. This rhythm was not always understood. For most of history, each appearance of the comet was seen as a singular, isolated event. It was a portent, a message from the heavens, a fiery star that appeared without warning and vanished just as mysteriously. People did not know that the brilliant visitor of one lifetime was the very same object that had graced the skies of their ancestors. They lacked the cosmic perspective to see the journey as a whole, to understand that what they were witnessing was but a brief, bright moment in a vast, repeating cycle. The idea that this celestial stranger was, in fact, a familiar neighbor on a very long and predictable path was a realization that would come much later, and it would change our relationship with the cosmos forever. The rhythm of its return transforms the comet from a terrifying omen into something far more comforting. It becomes a part of a celestial clockwork, a grand and elegant dance of gravity and motion. Its 76-year cycle is a human measure of time. Empires rise and fall between its visits. Technologies that would have seemed like magic in one appearance are commonplace by the next. And yet, the comet remains the same, a silent constant against the backdrop of our ever-changing world. It is a gentle reminder of the vast, slow, and orderly processes that govern the universe. It teaches us a different sense of time, one that is not measured in the frantic pace of a single day, but in the patient, looping journey of a celestial body through the quiet emptiness of space. This rhythm is the first clue to understanding its nature, the first hint that it is not just a random wanderer, but a true member of our solar system, bound by the same laws of motion that govern our own planet. For thousands of years, the comet was a nameless spectre. It was simply the Great Comet, or the long-haired star, a celestial event described by its appearance rather than its identity. The idea that it could have a name, a singular identity, would have been a foreign concept, for how can you name something that appears only once? The great shift in understanding, the moment when this recurring visitor finally received its name, did not come from a sudden, dramatic discovery, but from a quiet and patient act of intellectual curiosity. The story of the comet's name is the story of an English astronomer named Edmund Halley. In the late 17th and early 18th centuries, the scientific world was alive with a new understanding of the universe, thanks in large part to the work of Isaac Newton and his universal law of gravitation. For the first time, humanity had the mathematical tools to understand the elegant, invisible forces that governed the motion of the planets. Halley, a contemporary and friend of Newton, became fascinated with the records of comets. He believed that these mysterious visitors were not supernatural omens, but physical objects, bound by the same gravitational laws as the Earth and the other planets. He undertook a meticulous and patient task. He gathered all the historical records of comet sightings he could find, stretching back for centuries. He was particularly interested in a bright comet that had appeared in the year 1682, one that he had observed himself. As he carefully calculated the orbits of this and other comets from the past, he began to notice a remarkable pattern. He found that the path of the 1682 comet was strikingly similar to the paths of comets that had been recorded in 1531 and 1607. A quiet, profound realization began to dawn on him. These were not three separate comets. They were three appearances of the very same object, returning to our skies on a regular, predictable schedule. He realized he was looking at a single celestial body, tracing a long, looping path around the sun, a journey that took approximately 76 years to complete. Based on this insight, he made a bold and simple prediction. The comet would return again in the year 1758. Edmund Halley did not live to see his prediction come true. He passed away in 1742, but his quiet work had set in motion a new way of seeing the cosmos. As the year 1758 approached, astronomers across Europe turned their telescopes to the sky, waiting. And then, on Christmas night of that year, a German amateur astronomer named Johann Georg Palitzsch spotted it. The comet had returned, just as Halley had foretold. It was a triumphant moment, not of spectacle, but of quiet understanding. It was proof that the universe operated on principles that could be understood through patient observation and reason. In honor of the man who had first understood its true nature, the comet was finally given a name: Halley's Comet. Part-owned, the fading glow, 750-900 words. After gracing our skies for weeks or even months, a slow and inevitable change begins to occur. The comet, having made its closest and most intimate approach to the sun, begins its long journey back into the cold and the dark. The brilliant spectacle that so captivated observers on Earth begins to fade, like the embers of a dying fire. This gentle departure is as much a part of its story as its bright arrival, and it is in this fading glow that we find the central question of our journey tonight. As the comet moves away from the sun, the source of its transformation, the process that gave it life and light, begins to reverse. The sun's energy, which had been warming the comet's icy heart and causing it to release vast clouds of gas and dust, becomes weaker with every passing day. The glowing atmosphere around the nucleus, the coma, begins to shrink. The magnificent tails, which may have stretched for millions of miles across the solar system, start to diminish, losing their brilliance and their scale. The comet does not simply vanish, it performs a slow, graceful fade, gradually receding into the background of stars from which it emerged. From our vantage point on Earth, we would watch it night after night. A little dimmer, a little smaller, its journey carrying it farther and farther away. Soon, it would become too faint to be seen with the naked eye. An observer with a small telescope might be able to follow it for a while longer, a tiny, fuzzy patch of light moving silently against the fixed stars. But eventually, even for our most powerful instruments, it would disappear completely. It would cross the orbit of Mars, then the asteroid belt, and journey out past the great gas giants Jupiter and Saturn. It would continue to travel outward past Uranus and Neptune into the twilight realm of our solar system, a place of profound cold and near-perfect darkness. This fading glow is not an ending, but a transition. The comet is not dying, it is merely returning to its natural state. It is going back to a place where it is no longer an active, brilliant object, but a dormant, frozen one. It is returning to a state of hibernation, its icy body preserved in the deep freeze of the outer solar system. It is on this long, lonely road outward that the true scale of its journey becomes apparent. It is not just traveling beyond the planets we know. It is returning to a home that is so distant, so vast, and so different from the warm inner solar system that it challenges our very definition of where our solar system ends. The fading glow, therefore, is an invitation to wonder. As we watch it disappear into the blackness, we are left with a quiet, peaceful question: where is it going? What is the nature of its ultimate destination? We know its journey is a loop, a great repeating cycle. So, to what place must it travel before the sun's gravity inevitably begins to pull it back once more? Its departure is not a farewell, but a promise of return, and it is the first step in a journey that will take us, in our imaginations, to the very edge of our solar system, to the place where this familiar stranger truly belongs. The departure of Halley's Comet, its slow fade into the imperceptible depths of space, leaves us with a sense of profound and gentle curiosity. We have traced its history in our skies, we have understood the rhythm of its return, and we have followed its journey back out past the familiar signposts of the planets. Now, we arrive at the heart of our exploration, the central and most peaceful question of all: where did it really come from? This is not just a question of its last known location, but a deeper inquiry into its birthplace, the ancient reservoir from which it was sent on its very first journey toward our sun. For a long time, the origins of comets were a complete mystery. They seem to be ethereal visitors from interstellar space, passing through our solar system once, never to return. But the work of Edmund Halley and those who followed him proved that at least some comets, like Halley itself, were bound members of our solar system, held on vast, looping orbits by the sun's gravity. This realization, however, only deepened the mystery. If they were part of our solar system, where did they reside? They clearly did not orbit among the planets. Their paths were too long, too stretched out. Their home had to be somewhere else, somewhere far more distant. The first hints of an answer came from studying the paths of many different comets. Astronomers noticed that comets seemed to fall into two main categories. There were short-period comets which, like Halley, completed their orbits in less than 200 years. Then there were long-period comets which had orbits that were thousands or even millions of years long. These long-period comets seemed to come from all directions in the sky, not just from the flat plane in which the planets orbit. This suggested that their source was not a belt or a ring, but a vast spherical shell surrounding the entire solar system. This idea led to the first part of our answer. In the mid-20th century, a Dutch astronomer named Jan Oort proposed the existence of a theoretical, immense cloud of icy bodies at the very edge of the solar system, a place we now call the Oort cloud. He suggested that this was the primordial home of the long-period comets. This cloud would be a place of unimaginable cold and darkness, a vast spherical swarm of trillions of dormant comets, loosely held by the sun's gravity. It would represent the true boundary of our solar system, the final frontier of the sun's gravitational influence. But what about comets like Halley? Its orbit of 76 years is long by human standards, but very short compared to the comets from this distant cloud. This led to the proposal of a second, closer reservoir of comets, a region just beyond the orbit of Neptune. This region, a flattened, donut-shaped ring of icy bodies, came to be known as the Kuiper Belt. It was thought to be the source of the short-period comets. For a time, it was believed that our journey's end lay here, that Halley's comet was a resident of this icy outer planetary disk. However, the more astronomers studied Halley's specific path, the more they realized it was unique. While its period is short, its orbit is highly unusual. It travels backward compared to the planets, and its path is tilted at a steep angle to their orbital plane. The orbits of objects from the Kuiper Belt generally do not look like this. Instead, Halley's orbit looks much more like that of a long-period comet that has had its path altered over time. This suggests that Halley's comet is not originally from the Kuiper Belt, but is, in fact, an ancient visitor from the far more distant Oort cloud. It is believed to be a long-period comet that, on one of its journeys through the inner solar system, passed close enough to one of the giant planets, like Jupiter, to have its orbit gravitationally altered, capturing it into the much shorter 76-year loop we see today. So, our question of origin has a wonderfully layered answer. Halley's current behavior makes it seem like a short-period comet, but its true ancient home, its ultimate birthplace, lies in that vast, spherical, and utterly mysterious realm at the very edge of the sun's family. Our journey, therefore, must take us there. To understand the comet's journey from its distant home to our night sky, we must first picture the path it travels. This path is not a straight line, nor is it a perfect circle. It is an ellipse, a beautiful, elongated loop that carries the comet on a grand tour of our solar system, from its warmest heart to its coldest, most distant frontiers. An ellipse can be thought of as a stretched or flattened circle. Imagine 2 points in space. If a circle has one central point, an ellipse has two, which are called foci. The sun does not sit in the center of the comet's orbit. Instead, it resides at one of these two focal points. This simple geometric fact is the key to the comet's entire story. Because the sun is at one focus, the comet's distance from it is constantly changing throughout its journey. For a significant portion of its orbit, it is incredibly far away, moving slowly through the frigid darkness of the outer solar system. Then, as it rounds the far end of its path and begins to fall back inward, it starts to accelerate, pulled by the sun's ever-increasing gravitational influence. It moves faster and faster, reaching its maximum speed as it whips around the sun at its closest point, a point known as perihelion. Having passed this point, It begins its slow climb back outward, fighting against the sun's gravity, gradually losing speed until it once again reaches its most distant and slowest point, known as aphelion, before the whole cycle begins anew. The shape of Halley's ellipse is extreme. Its eccentricity, a measure of how stretched out it is very high, close to the maximum possible for a closed orbit. This is why its journey is one of such dramatic contrasts. At its most distant point, its aphelion, Halley's comet travels out to a distance of about 35 astronomical units from the Sun. An astronomical unit is the distance from the Earth to the Sun. So this means the comet travels 35 times farther from the Sun than we are, out beyond the orbit of the most distant planet, Neptune. In this realm, the Sun would appear as just an incredibly bright star, its warmth barely felt. In contrast, at its closest approach, its perihelion, the comet comes to within about half an astronomical unit of the Sun, closer than the orbit of Venus. This great elliptical path is like an invisible roadway in space, a channel carved by the laws of gravity. It is a path of solitude. For the vast majority of its 76-year journey, the comet is alone in the dark, a frozen, dormant object. It is only for a few short months, during its frantic rush around the Sun, that it awakens and becomes the brilliant spectacle we can see from Earth. The rest of the time it is simply traveling, following the silent, elegant mathematics of its orbit. Understanding this path is like learning the grammar of the comet's story. It explains the rhythm of its return, it accounts for its changing speed, and it sets the stage for its dramatic transformation. It is a cosmic dance, choreographed by a single, powerful partner, the Sun, and it is a dance of immense scale, patience, and beauty. For decades, the comet journeys through the profound cold of the outer solar system, a silent, dark, and frozen world. But as it follows its great elliptical path back inward, it begins to feel a change. The Sun, once a distant point of light, grows steadily larger and brighter. A gentle, imperceptible warmth begins to touch its ancient, icy surface. This is the beginning of the comet's awakening, a slow and beautiful transformation that occurs as it enters the Sun's warm embrace. This moment of closest approach is called perihelion. As Halley's comet hurtles toward this point, the Sun's energy intensifies dramatically. The surface of the comet's nucleus, which is a mixture of water, ice, frozen gases like carbon dioxide and ammonia, and dark dust, begins to warm. In the near vacuum of space, this warming does not cause the ice to melt into liquid. Instead, it undergoes a process called sublimation, transforming directly from a solid into a gas. This is the key to the comet's spectacular appearance. As the ices sublimate, they erupt from the surface in jets, carrying with them particles of dust that have been trapped in the ice for billions of years. This mixture of gas and dust forms a vast glowing cloud around the nucleus, an ethereal atmosphere known as the coma. The coma can grow to be enormous, sometimes becoming larger than the planet Jupiter, all while the solid nucleus at its heart may only be about 15 kilometers, or 9 miles, across. The Sun's light illuminates this cloud, causing it to glow with a soft, fuzzy light, making the tiny, dark nucleus visible from hundreds of millions of miles away. But the transformation does not stop there. The Sun is not just a source of light and heat. It also emits a constant stream of charged particles called the solar wind. This wind, along with the pressure of sunlight itself, pushes on the material of the coma, sweeping it back to form the comet's magnificent tails. There are typically 2 distinct tails. The dust tail is made of the larger, heavier particles of dust. These particles are pushed back gently by the pressure of sunlight and tend to follow the comet's curved orbital path, creating a broad, diffuse, and often slightly curved tail that can be yellowish-white in color. The second tail is the ion tail, or gas tail. It is made of gases from the coma that have been stripped of electrons or ionized by the Sun's ultraviolet light. These charged particles are then powerfully pushed directly away from the Sun by the solar wind, forming a long, straight, and often bluish tail. Because it points directly away from the Sun, the ion tail acts like a celestial windsock, showing the direction of the solar wind at that point in space. This means that as the comet moves away from the Sun, its tails actually travel in front of it. The sun's embrace is a moment of both creation and consumption. It is what gives the comet its beauty, but it is also a process that slowly wears the comet away. With each pass, it loses a layer of its ice and dust, a small fraction of its ancient self, which it leaves behind to trail along its orbit. It is a gentle, transformative fire that awakens the sleeping giant for a brief, glorious season of light. Having survived its fiery passage around the sun, its moment of perihelion, the comet does not stop. Its immense velocity carries it forward, and it begins the next phase of its journey, the long, slow climb back out of the sun's deep gravitational well. This part of its voyage is a mirror image of its approach, but in reverse. It is a journey of diminishing energy, of fading light, and of a return to the profound quiet of deep space. As the comet moves away from the sun, the forces that gave it its brilliant form begin to weaken. The sunlight becomes less intense, and the solar wind less powerful. The surface of the nucleus begins to cool, and the process of sublimation, the heart of the comet's activity, slows down. The jets of gas and dust that erupted from its surface become less vigorous. And then, one by one, they cease. The coma, that vast, glowing atmosphere, begins to shrink as it is no longer being replenished from the nucleus. The magnificent tails, no longer being fed by the coma, start to dissipate and fade. The comet is, in essence, putting itself back to sleep. This journey outward is a constant battle against the sun's gravity. While the comet is moving away, the sun is still pulling it back, trying to keep it from leaving. This constant pull acts as a brake, causing the comet to gradually slow down. It reached its maximum speed as it whipped around the sun, but now, with every million miles it travels, its velocity decreases. This deceleration is slow and patient, a process that will take more than 3 decades to complete. The frantic, high-speed dash through the inner solar system gives way to a much more stately and unhurried pace. We can imagine the comet on this journey, a silent, fading spectre. It climbs past the orbit of Venus, then Earth, then Mars. It crosses the asteroid belt, a region of rocky debris that it navigates with ease due to the vast emptiness of space. With each step of this outward climb, the universe around it becomes colder and darker. The vibrant, dynamic inner solar system is left behind, and the lonely, quiet expanse of the outer solar system opens up before it. It is returning to its native environment, the realm of ice and shadow. The fading glow we would see from Earth is a direct reflection of this journey, a visual representation of the comet's slow retreat from the life-giving, but also life-consuming, energy of the sun. It is a long goodbye, a gradual and peaceful transition from a spectacular celestial event back into a simple, dormant ball of ancient ice, coasting silently toward the distant frontiers of our solar system. The comet's slow climb outward takes it into a realm of giants. After crossing the asteroid belt, Halley's comet enters the domain of the great gas planets, the colossal worlds that dominate the outer solar system. These planets, Jupiter, Saturn, Uranus, and Neptune, act as silent, gravitational signposts on the comet's long road home, and their influence has played a crucial role in shaping the very orbit it travels. The first giant it encounters on its way out is the undisputed king of the solar system, Jupiter. Jupiter is so massive that its gravity has a profound effect on the paths of smaller bodies like comets and asteroids. It acts as a great cosmic shepherd, its gravity deflecting objects, and sometimes capturing them. It is believed that a close encounter with Jupiter, or one of the other gas giants, long ago is what transformed Halley's comet from a long-period visitor from the Oort cloud into the short-period comet we know today. The planet's immense gravity would have acted like a gravitational brake, robbing the comet of some of its orbital energy and pulling it into a much smaller, tighter loop around the sun. So, as Halley passes Jupiter's orbit, it is passing the very architect of its current journey. Leaving Jupiter behind, the comet continues its slow outward coast. The next milestone is the magnificent ringed planet, Saturn. From this distance, the sun is beginning to look smaller, and the temperature of space has dropped to a level where even the most volatile ices are completely and permanently frozen. The comet is now fully dormant, a silent, dark nucleus, showing none of the activity it displayed in the inner solar system. It is a world asleep, preserving its ancient secrets in a deep cosmic freeze. The journey continues, pushing ever farther into the dim twilight of the solar system. It crosses the orbit of Uranus, the seventh planet, a pale blue-green world tilted on its side. Here, the sun's light is nearly 1,000 times fainter than it is at Earth. The darkness is becoming profound, the silence absolute. The comet is now moving very slowly, its momentum from its perihelion pass nearly spent, coasting through a region of space that feels almost empty. Finally, it reaches the last of the giant planets, the deep blue world of Neptune. This is the great frontier of the planetary part of our solar system. Beyond Neptune lies a different realm, a vast and largely unexplored territory. By the time Halley's comet crosses Neptune's path, it has been traveling away from the Sun for more than 35 years. It has completed the planetary leg of its journey and is now entering the true wilderness of the outer solar system, the place where its long, elliptical path will finally reach its outermost point. The gas giants, these silent and powerful worlds, have watched it pass, their gravity giving it a final gentle nudge on its way, shaping its path in subtle ways that will determine the precise timing of its return, decades from now. Having passed beyond the orbits of all the major planets, Halley's comet continues its silent voyage into the deep, cold dark. It is now in a region of space that is almost unimaginably empty and remote. After approximately 38 years of climbing away from the Sun, the comet finally reaches the pinnacle of its orbit, the farthest and slowest point of its journey. This point is called aphelion. It is a place of profound stillness, a moment of cosmic pause before the great fall back toward the Sun begins anew. The aphelion of Halley's comet occurs at a distance of about 35 astronomical units from the Sun. This places it well beyond the orbit of Neptune, which circles the Sun at an average distance of about 30 astronomical units. Here, at the very edge of the planetary solar system, the universe takes on a completely different character. The Sun, which dominates our sky and warms our world, has shrunk to a brilliant, star-like point of light. It is still the brightest object in the sky by far, but its energy and warmth are now incredibly faint. The temperature here is only a few tens of degrees above absolute zero, the coldest it is possible to get. In this state of extreme cold, the comet is perfectly preserved. It is a solid, inert object, a nucleus of ice and dust, perhaps only about 15 kilometers long and 8 kilometers wide. Its surface is incredibly dark, blacker than coal, reflecting only a tiny fraction of the faint sunlight that reaches it. This is because its surface is coated with a layer of dark, organic dust. The heavier material left behind after the more volatile ices have sublimated away on its many trips near the Sun. There are no jets, no coma, no tails. The brilliant spectacle of the inner solar system is a distant memory. Here, at aphelion, the comet reveals its true underlying nature, a small, dark, and ancient world, hibernating in the cosmic deep freeze. Its speed at this point is at its absolute minimum, having fought against the Sun's gravity for its entire outward journey. Its momentum is almost entirely spent. It is moving at a speed of less than 1 kilometer per second, a mere walking pace compared to the incredible velocities it achieves near the Sun. For a brief period, it seems to hang almost motionless in the darkness, balanced precariously between its outward momentum and the Sun's relentless gravitational pull. It is the turning point of its journey. It has climbed as high as its orbit will allow, and from this moment on, it can only fall. This moment of aphelion is a moment of perfect, serene solitude. The giant planets are now far away, their gravitational influence much weaker. The comet is alone in the vast, quiet emptiness. It is a place where time itself seems to slow down. The 76-year cycle, which feels so long to us, is defined by this slow, patient journey out to this lonely turning point and back again. Spending a moment here, in our imaginations, gives us a true appreciation for the scale of the comet's journey. It is not just visiting our part of the solar system. It is a true resident of these dark, cold outer reaches, and its brilliant appearance in our sky is just a brief, fiery interruption of its otherwise quiet, frozen existence. From here, the sun's gravity, though faint, is still dominant, and it will now begin to gently, inexorably pull the comet back, starting the 38-year-long fall that will eventually bring it back to our skies once more. Even here, at aphelion, 35 times farther from the sun than the Earth, in a realm of profound cold and darkness, the comet is not truly free. It is still held firmly in the sun's gravitational embrace. This unseen influence, a gentle but persistent tether, is the force that defines the comet's entire existence. It is what ensures that its journey is a closed loop, that its departure is always a promise of return. The sun's gravity reaches out across billions of miles of empty space, shaping the comet's path and ensuring that it remains a member of our solar system family. Gravity is a force that weakens with distance, but it never truly disappears. Even at this immense remove, the sun's mass creates a subtle curvature in the fabric of space-time, a gentle slope that the comet must follow. Having reached the slowest point in its orbit, the comet has no more outward momentum to fight against this pull. The balance has shifted, and the journey back inward now begins. The fall will be imperceptibly slow at first. For years, the comet will barely seem to move, gradually picking up speed as it travels along the shallowest part of the gravitational gradient. But the process is inevitable. The unseen influence of the sun dictates that its journey must now be one of acceleration, a slow gathering of speed that will continue for the next 3.5 decades. This gravitational tether, however, hints at something more. The comet's orbit, this vast ellipse, is itself contained within an even larger structure. While the sun's gravity is dominant out here, it is not the only gravitational force at play. The combined gravity of the entire Milky Way galaxy exerts a subtle tidal force, and occasionally, other stars pass by our solar system at immense distances. For an object on a stable, relatively short orbit like Halley's Comet, these external influences are minor, causing only tiny perturbations. But this hints at the existence of a region even farther out, a place where the sun's gravitational hold is so tenuous that these other forces become significant. The great elliptical path of Halley's Comet, therefore, can be seen as an inner journey within a much vaster cosmic territory. It is traveling at the very edge of the planetary realm, but it is still deep within the sun's sphere of influence. This sets up the next stage of our own journey of understanding. To find the comet's true origin, we must travel in our minds beyond this elliptical path, beyond the point of aphelion, and into the regions where the sun's unseen influence becomes so fragile that it can be disturbed by the gentle whispers of the galaxy itself. Halley's stable, repeating orbit is a clue that it has been captured into this relatively small path. But its composition and unusual trajectory tell us that its story began somewhere else, in a place much farther away, a place we must now explore. The unseen influence that holds it in its 76-year loop is the very same influence that holds the key to its ancient home. To truly understand the comet, we must look past its magnificent temporary display of light and journey to its very core. Deep within the glowing coma, hidden from our view, lies the source of it all, the nucleus. This is the comet's solid, permanent body, its sleeping heart. For most of its existence, this nucleus is all that the comet is: a small, dark and frozen world, coasting silently through the void. The common description of a comet nucleus is a dirty snowball, a phrase coined by astronomer Fred Whipple. And while beautifully simple, it is also profoundly accurate. The nucleus is a conglomerate, an amalgamation of water ice, frozen gases like carbon monoxide, carbon dioxide, methane and ammonia, all mixed together with dark, rocky dust and organic compounds. The nucleus of Halley's Comet is surprisingly small, only about 15 kilometers long and 8 kilometers wide and thick, roughly the size of a small city or a large mountain. It is not spherical but has an irregular, elongated shape often compared to a peanut or a potato. Its surface is not a pristine, reflective white, as one might expect from a body of ice. Instead, it is one of the darkest objects in our solar system, with a surface as black as velvet or coal. This is because, over countless passes near the sun, the more volatile ices on the very surface have sublimated away, leaving behind a crust of dark, dusty material and complex organic molecules. This dark crust acts as an insulator, protecting the vast reserves of ice that lie just beneath the surface from the sun's heat. This sleeping heart is not a solid, uniform object. It is thought to have a very low density, suggesting it is not a solid block of ice and rock, but rather a porous, fluffy aggregate of smaller pieces, loosely held together by their own weak gravity. It is a fragile construction, a cosmic iceberg that is more like a loosely packed snowball than a hard, dense rock. This structure is a direct consequence of its formation in the earliest days of the solar system. It is a primordial remnant, a piece of the original solar nebula that never got incorporated into a planet. It formed in a region of space so cold and so far from the sun that these volatile ices could condense and clump together, gently accumulating over time. For this reason, the nucleus is a time capsule. Locked within its frozen interior is the original chemical recipe of our solar system, preserved in a near-perfect state for over 4.5 billion years. The water within it is ancient water. The organic molecules are the very same types of building blocks that, on a young Earth, may have played a role in the origin of life. To study the composition of a comet's nucleus is to read a chapter from the very first page of our solar system's history. When the comet is far from the sun, in the cold of the outer solar system, this heart is truly sleeping. It is inert, unchanging, a silent guardian of ancient secrets. It is only when it journeys inward that this sleeping heart awakens, and the pristine, ancient material from within is released, creating the beautiful, transient spectacle that we see from so far away. The entire grand display of the coma and tails is just the comet breathing, exhaling a tiny fraction of its ancient self into the light. As the sleeping heart of the comet awakens in the warmth of the inner solar system, the first and most immediate feature to appear is the coma. This is the vast, glowing cloud of gas and dust that completely envelops the nucleus, transforming the small, dark iceberg into a luminous, ghostly presence in the night sky. The coma is, in essence, the comet's temporary atmosphere, an atmosphere of light born from the sublimation of its ancient ices. The process begins as sunlight heats the dark surface of the nucleus. The ices just beneath the crust turn directly into gas and burst forth in powerful jets, erupting from fissures and active regions on the surface. These jets are not uniform. They are localized explosions of activity, and their force can be strong enough to gently alter the comet's rotation and even nudge it slightly off its purely gravitational path. These eruptions release not just gas, but also vast quantities of fine dust particles that were embedded within the ice. This liberated gas and dust expands outward from the nucleus into the vacuum of space, forming a spherical cloud. This cloud is the coma. While the nucleus itself is tiny, the coma can become immense, often growing to be hundreds of thousands of kilometers in diameter. For a particularly active comet like Halley, its coma can even temporarily become larger than the sun itself. Yet, this vast atmosphere is incredibly tenuous, far less dense than the thinnest air on Earth. It is a near-perfect vacuum, filled with a sparse but energetic population of molecules and dust grains. The coma glows for two primary reasons. First, the countless tiny dust particles within it are very effective at reflecting sunlight. They create a diffuse, hazy glow, a soft, white or yellowish light that forms the main visible body of the comet as seen by the naked eye. Second, the gas molecules within the coma are energized by the sun's ultraviolet radiation. This energy excites the electrons within the molecules, and as they fall back to their normal state, they emit light of specific colors, a process known as fluorescence. This is what can give the inner part of the coma a greenish or bluish tint in long-exposure photographs, a ghostly light that comes from the gas itself. The coma is a world of constant dynamic change. It grows in size and brightness as the comet approaches the sun and shrinks and fades as it moves away. It is shaped and sculpted by the pressure of sunlight and the solar wind, which begin to sweep its material away from the sun, forming the first wisps of what will become the comet's tails. The coma is the bridge between the solid, sleeping heart of the nucleus and the spectacular, flowing tails. It is a soft, ethereal shroud, a temporary halo that makes the invisible visible and allows us to witness the slow, graceful exhalation of an ancient world as it passes through the warmth of our sun. Flowing away from the luminous atmosphere of the coma is the first and often most visually prominent of the comet's two great appendages, the dust tail. This is the feature that has historically given comets their name, from the Greek word kometes, meaning long-haired. The dust tail is a vast, shimmering river of fine particles, a gently curved trail of cosmic dust that marks the path the comet has traveled. It is a silent, graceful testament to the comet's slow dissolution in the sunlight. The dust tail is composed of the solid particles, the dirt from the dirty snowball, that are lifted off the nucleus along with the sublimating gas. These particles range in size from microscopic smoke-like grains to small pebbles. Once they are released into the coma, they are no longer bound to the nucleus. They are now independent objects, each with its own orbit around the sun. However, they are also subjected to a gentle but persistent force, the pressure of sunlight itself. Photons, the particles of light streaming from the sun, act like a very gentle wind pushing on these tiny dust grains. This solar radiation pressure is very weak, but in the frictionless environment of space, it is enough to push the dust particles away from the sun and out of the coma. Because the dust particles are relatively heavy compared to individual gas molecules, they are not pushed as forcefully. They tend to retain much of their original orbital momentum, continuing to travel along a path very similar to that of the comet's nucleus. The result is that the dust particles lag behind the nucleus in its orbit, forming a long, broad, and often gently curved tail. The curve of the dust tail is a beautiful visual representation of the laws of motion. The largest, heaviest particles are pushed the least by sunlight and stay closest to the comet's original path. The smallest, lightest particles are pushed the most, ending up farther from the nucleus. This sorting of particles by size is what creates the tail's broad, fan-like shape. The curvature arises because while the dust is being pushed away from the sun, it is also continuing to move along its vast, curved orbit. The tail we see is a composite image of where the dust particles have been over the past several days or weeks. The dust tail shines purely by reflected sunlight. It is, in essence, a cloud of tiny natural satellites, each one reflecting a minuscule amount of light, but their combined effect creates the beautiful, glowing appendage we see from Earth. Its color is typically a soft, yellowish white, the same color as the sunlight it is reflecting. It can stretch for tens of millions of kilometers, a silent, luminous wake that follows the comet through the inner solar system, a trail of breadcrumbs left by a visitor from the deepest, darkest parts of space. While the gently curving dust tail is often the brightest and most obvious feature of a comet, there is a second, more ethereal and mysterious tail that frequently accompanies it, the ion tail. This tail is dramatically different in both its appearance and its origin. Where the dust tail is broad, curved, and yellowish white, the ion tail is typically narrow, straight as an arrow, and often glows with a distinct ghostly blue light. It does not follow the comet's path, but instead points directly away from the sun, like a cosmic compass needle. The ion tail is not made of dust, but of gas. It begins with the volatile gases like water, carbon monoxide, and carbon dioxide that sublimate from the nucleus and form the coma. As these gas molecules drift in the coma, they are exposed to the sun's intense ultraviolet radiation. This high-energy light is powerful enough to knock electrons off the gas molecules, a process called ionization. The molecules are no longer electrically neutral. They now have a positive charge, turning them into what are known as ions. This is where the second major force from the sun comes into play, the solar wind. The solar wind is a fast-moving stream of charged particles, protons and electrons that constantly flows outward from the sun at hundreds of kilometers per second. Because the gas in the coma is now made of charged ions, it can be powerfully grabbed and carried along by the magnetic field embedded in the solar wind. The solar wind is far more powerful in its effect on these ions than the gentle pressure of sunlight is on the dust particles. It sweeps up the ionized gas from the coma and pushes it straight back directly away from the sun at very high speeds. This is why the ion tail is so straight. It acts as a perfect tracer for the direction of the solar wind at the comet's location. Regardless of which way the comet itself is moving in its orbit, the ion tail will always point away from the sun. This means that after the comet passes its closest point to the sun and begins moving away, its ion tail actually travels in front of it. A strange and beautiful consequence of celestial mechanics. The ghostly blue color of the ion tail is also a result of this energetic process. It is a form of fluorescence. The ions, particularly carbon monoxide ions, absorb sunlight and then re-emit it at specific wavelengths, with the most prominent one being in the blue part of the spectrum. The structure of the ion tail is often complex and dynamic, showing knots, streamers, and kinks. These features are a direct reflection of changes and turbulence in the solar wind, meaning that by observing the ion tail, we are actually watching the weather of interplanetary space. It is a delicate, beautiful, and informative structure. A straight blue line of gas painted against the dark, a silent testament to the powerful and invisible forces that emanate from our star. The brilliant spectacle of Halley's Comet as it passes through the inner solar system is a sign of its own slow, graceful, and inevitable transformation. Each visit to the sun is an act of self-consumption. The very process that gives the comet its life and beauty is also the process that is slowly wearing it away. With every 76-year cycle, it leaves a small piece of itself behind, scattered along its orbital path. This is not a violent or destructive end, but a gentle cosmic aging, a slow and patient dissolution that plays out over immense timescales. On each pass, as the sun's warmth causes its ices to sublimate, the comet loses a layer of material from its nucleus. It is estimated that Halley's Comet loses a layer perhaps 1 to 3 meters, or 3 to 10 feet, thick from its surface during each perihelion passage. This may not sound like much for a body that is many kilometers across, but over thousands of orbits and hundreds of thousands of years, this slow erosion will have a profound effect. The comet is, quite literally, evaporating into space. The material it loses, the gas that forms the ion tail, and the dust that forms the dust tail, does not simply vanish. It continues to orbit the sun, spreading out along the comet's path like a ghostly river of debris. This is the comet's legacy, a permanent record of its many journeys. We will explore this legacy in more detail later, but for now, it is enough to know that every gram of material shed by the comet adds to this vast, invisible structure. This slow transformation means that the comet we see today is not quite the same object that was seen by observers in the year 1066 or in 240b. It is slightly smaller, slightly less massive, and perhaps slightly less active than it was in the distant past. It is an aging world. Eventually, after tens or even hundreds of thousands of more years, this process will reach its conclusion. One possibility is that the comet will exhaust all of its volatile ices. With no more ice to sublimate, the jets will cease, and the comet will no longer be able to produce a coma or a tail. It will become a dark, inert object, a dead comet nucleus that is little more than a clump of rock and dust, indistinguishable from a small asteroid, continuing to follow its elliptical path in silence. Another possibility is that the slow loss of material will weaken its internal structure, causing it to break apart completely, its remains spreading out to form a dense stream of dust and pebbles. In either case, the end is not an explosion or a cataclysm, but a quiet fading, a peaceful return to the constituent stardust from which it was formed. This gentle life cycle reminds us of the transient nature of all things, even on a cosmic scale. The beauty of Halley's Comet is the beauty of a fleeting moment, a temporary awakening in a very long life that is, itself, finite. Long before it was understood as a repeating visitor, long before it bore the name of an English astronomer, Halley's Comet was a silent and recurring character in the story of humanity. To look back at its historical appearances is to see a series of echoes in ancient skies, moments when our ancestors paused their daily lives, looked up in awe or fear, and recorded the passage of a mysterious, luminous wanderer. These ancient records are more than just astronomical data. They are moments of shared human experience, a connection to the distant past through the simple act of witnessing a celestial event. The earliest confirmed sighting of Halley's comet comes from Chinese astronomers in the year 240 BC. The records of the Grand Historian describe a broom star that appeared in the east and moved north. For the ancient Chinese, the sky was a celestial bureaucracy, a mirror of the earthly empire, and every event had meaning and significance. Comets were carefully observed and recorded, their positions, brightness, and the length and direction of their tails all noted with meticulous care. These records, kept by court astronomers for centuries, provide us with the most complete and continuous history of the comet's appearances. But the Chinese were not the only ones watching. In ancient Babylon, astronomers recorded the comet's appearance on clay tablets in the years 164 BC and 87 BC. These cuneiform records, preserved for millennia in the dry earth, speak of a celestial object that was seen for many days, a silent and persistent light in the heavens. These were cultures deeply attuned to the rhythms of the sky, and the appearance of something new and unexpected was an event of great importance, worthy of being inscribed into their most lasting records. As we move forward in time, the echoes continue. The comet appeared in 12 BC, around the time of the birth of Christ, though it is another comet which appeared a few years earlier that is more often associated with the Star of Bethlehem. Roman historians wrote of its passage, often linking it to significant events on Earth. Throughout history, the comet has been seen as a harbinger of change, a celestial omen. Its appearance was often associated with the death of kings, the fall of empires, or the coming of plagues and famines. This was not because the comet had any physical influence on earthly affairs, of course, but because of a deep-seated human need to find meaning and connection in the grand, silent events of the cosmos. The sudden arrival of a fiery sword in the sky was a profound and unsettling event for people who believed the heavens were a realm of perfect, unchanging order. These ancient sightings represent a different kind of knowledge, one based not on physical understanding but on myth, story, and a sense of wonder. When we read these old accounts, we are not just learning about the comet's orbit, we are connecting with the minds of our ancestors. We can feel the awe they must have felt, standing under a dark, pre-industrial sky, seeing this luminous ghost drift silently across the familiar constellations. It is a shared heritage, a reminder that for all the ways our world has changed, the sky above us and the silent visitors that pass through it remain a source of profound and universal wonder. Of all the historical appearances of Halley's comet, perhaps none is more famous or more vividly preserved than its passage in the year 1066. This was a year of immense upheaval and change in England, the year of the Norman conquest. And as fate would have it, the comet chose this pivotal moment in history to make one of its most spectacular appearances, an event that was immortalized not in an astronomical text, but in a magnificent work of art, the Bayeux Tapestry. The Bayeux Tapestry is not actually a tapestry, but a long embroidered cloth that tells the story of the Norman invasion of England, culminating in the Battle of Hastings. In one of its most famous panels, we see a group of Englishmen pointing up in terror at the sky. Above them, a fiery star-like object with a streaming tail dominates the scene. The Latin inscription reads, Isti mirant stella, which means, these men wonder at the star. This star was Halley's comet. The comet appeared in the spring of 1066, just a few months before William the Conqueror launched his invasion from Normandy. For the English, led by King Harold, the comet was seen as a terrible omen, a celestial portent of disaster. The Anglo-Saxon Chronicle, a history of the time, described it as a portent such as men had never seen before, a long-haired star that shone for many nights. In the world of medieval Europe, the appearance of such an object was a clear and unambiguous sign of divine displeasure and impending doom. For King Harold, who had only recently taken the throne, it must have felt like the heavens themselves were turning against him. For William the Conqueror, across the English Channel in Normandy, the comet was interpreted in the exact opposite way. It was seen as a sign of his own destiny, a heavenly promise of his success. He used the appearance of the comet as a powerful propaganda tool, convincing his soldiers that God was on their side, that their invasion was fated to succeed. The comet thus became woven into the very fabric of the political and military events of that year. The depiction on the Bayeux tapestry is a powerful reminder of how our perception of the cosmos has changed. The men in the tapestry are not looking up with scientific curiosity. They are looking up with fear and wonder, seeing a message written in the language of divine power. For them, the comet was not a natural phenomenon to be studied, but a supernatural sign to be interpreted. And yet, their depiction of it is also a precious historical record. It allows us to pinpoint the comet's appearance in that year with great accuracy, and it provides a direct, visual link to an event that happened almost 1,000 years ago. When we look at that embroidered star, we are seeing the comet through the eyes of people from a vastly different time, a moment when a silent visitor from the edge of the solar system became an actor on the stage of human history. Throughout much of human history, the sky was seen as a realm of constancy and perfection. The stars were fixed in their constellations. The planets moved with predictable, godlike grace, and the sun and moon followed their eternal cycles. Into this divine order, the sudden and unannounced appearance of a comet was a profound disruption. It was an anomaly, a celestial stranger that did not follow the established rules. It is no wonder, then, that for thousands of years, comets were almost universally regarded as omens, as portents of great and often terrible change. The physical appearance of a comet lent itself easily to these interpretations. The bright, star-like head and the long flowing tail were often seen as a fiery sword hanging in the sky, a celestial weapon brandished by an angry god. It was seen as a cosmic broom, sent to sweep away the existing order, or it was a long-haired star, a sign of cosmic mourning. In a world where people looked to the heavens for guidance and meaning, the arrival of such a dramatic and unfamiliar object could only mean that the gods or the universe itself had something important, and usually dreadful, to say. This belief is woven through the historical records of Halley's comet. Its appearance was often chronicled alongside the major events of the time, not as a coincidence but as a cause. The Roman historian Josephus connected a comet that appeared in 66 AD, likely Halley's, with the destruction of Jerusalem. In 451 AD, its appearance coincided with the defeat of Attila the Hun, and it was seen by many as a celestial sign of his downfall. The famous appearance in 1066 was, as we have seen, interpreted as a direct harbinger of the Norman conquest. In 1301, the comet made another bright appearance. It is believed that this is the comet that the Italian painter Giotto di Bondone witnessed, and that it inspired his depiction of the Star of Bethlehem in his famous fresco, The Adoration of the Magi. In his painting, the star is not a traditional star shape, but a fiery, comet-like object, a powerful and realistic image that may be the first naturalistic depiction of the comet in art. Even here, the comet is a sign, a divine messenger heralding a world-changing event. This deep-seated need to see comets as portents speaks to a fundamental aspect of the human experience, our search for meaning, and our desire to feel connected to the cosmos. In a world that often felt chaotic and unpredictable, finding patterns and messages in the sky was a way of imposing a sense of order. It was a way of believing that the great events of the heavens were intimately connected to the small lives of people on Earth. We should not look back on these beliefs with a sense of superiority, but with a sense of gentle empathy. The fear and awe that our ancestors felt were born from the same sense of wonder that drives scientific inquiry today. It is the same human response to the profound mystery and majesty of the universe, simply expressed in a different language. The comet was a portent of change, not because it caused it, but because its silent, beautiful passage has always inspired humanity to look up and ponder its place in the grand cosmic story. For millennia, our relationship with the comet was one of passive observation and fearful interpretation. It was an object of myth and superstition, a celestial actor in human dramas. But slowly, patiently, over the course of centuries, a new way of seeing the sky began to emerge. The period leading up to Edmund Halley's great insight was a time of quiet revolution, a dawn of understanding where the tools of reason, mathematics, and careful observation began to peel back the veil of mystery that had always shrouded the cosmos. This great shift did not happen overnight. It was the culmination of the patient work of many individuals who began to chart the heavens with a new and unprecedented level of precision. In the 16th century, the Danish astronomer Tycho Brahe made some of the most accurate and detailed observations of the stars and planets ever recorded up to that time. When a great comet appeared in 1577, he used his instruments to carefully measure its position. He was able to show that the comet was much farther away than the moon, that it was a truly celestial object moving among the planets, not an atmospheric phenomenon, as had long been believed. This was a crucial step in demystifying comets, moving them from the realm of weather and omens into the realm of astronomy. A few decades later, the German astronomer Johannes Kepler, using Tycho's meticulous data, derived his 3 laws of planetary motion. He discovered that planets moved not in perfect circles but in ellipses, and he described the mathematical relationship between a planet's distance from the Sun and the speed of its orbit. Kepler himself applied his laws to comets, suggesting that they too traveled on paths that were governed by the Sun. He believed their paths were straight lines, however, which meant they would only pass through the solar system once. The idea of a repeating elliptical orbit for a comet had not yet been fully realized. The final and most crucial piece of the puzzle was provided by Sir Isaac Newton. In 1687, he published his Principia, which laid out the law of universal gravitation. This was the master key, the single elegant principle that explained everything from a falling apple to the orbits of the planets. Newton's law showed that the same force that held the moon in orbit around the Earth was what held the Earth in orbit around the Sun. It was a universal force, and it applied to all objects, including comets. Newton himself demonstrated that the great comet of 1680, a spectacular object he had observed, was moving on a parabolic orbit, a path consistent with his law of gravity. These were the giants on whose shoulders Edmund Halley stood. By the time he began his own work on comets, the intellectual foundation had been laid. The universe was no longer seen as a place of divine caprice, but as a vast, intricate machine, a cosmic clockwork that operated according to precise and knowable mathematical laws. The tools were now in place to finally understand the true nature of the long-haired star. The stage was set for one quiet, thoughtful astronomer to connect the dots, to look back at the scattered records of the past and see not a series of isolated events, but the single, continuous, and beautiful story of one comet's repeating journey. The story of how Halley's comet received its name is not a tale of dramatic action or sudden, startling discovery in the dead of night. It is something quieter, deeper, and in many ways more profound. It is the story of a single, powerful idea, born from the patient application of reason and the quiet contemplation of numbers. It is a moment of intellectual connection, where one mind, for the first time, bridged the centuries and saw a single, continuous thread running through what had always seemed to be isolated and unrelated events. Edmund Halley was a brilliant and versatile scientist, a man of immense curiosity who applied himself to everything from naval navigation to life expectancy tables. But his great passion, spurred on by his friendship with Isaac Newton, was the application of Newton's new laws of gravity to the heavens. While others were focused on the predictable, orderly motions of the planets, Halley was drawn to the wild, untamed mystery of comets. He firmly believed that they were not chaotic intruders, but were, like everything else, governed by the sun's gravitational pull. He set himself a monumental task: to gather every reliable historical observation of a comet that he could find, and to calculate the shape of its orbit. He compiled a list of 24 cometary appearances, meticulously calculating the orbital elements for each one based on the recorded observations. It was a painstaking process, a deep dive into the dry, mathematical descriptions of celestial positions. As he worked, he began to pay special attention to 3 specific comets, one observed by Petrus Appianus in 1531, another by Johannes Kepler in 1607, and a third, which he had observed himself, in 1682. He calculated the orbital path for each of these 3 apparitions, and as he compared the numbers, the quiet revelation began to unfold. The orbits were, for all practical purposes, identical. They were all traveling along the same great elliptical path through the solar system. The comets were all moving backward or retrograde compared to the planets. Their orbital planes were tilted at the same angle. They all reached their closest point to the sun at the same distance. The conclusion, to a mind prepared to see it, was inescapable. He was not looking at three different comets that happened to have similar paths. He was looking at three separate appearances of the very same object, returning to the inner solar system again and again, like a celestial clock, on a schedule of roughly 76 years. This was a moment of profound insight. It was the first time in history that anyone had proven that a comet could be a permanent member of our solar system, a periodic visitor on a closed, repeating path. Based on this realization, Halley made his now famous prediction. He proposed that the comet would be seen again, that it would return to our skies at the end of the year 1758 or the beginning of 1759. He was not entirely certain of the date, as he knew that the gravitational pulls of the giant planets, Jupiter and Saturn, would slightly alter the orbit, speeding it up or slowing it down. But he was certain that it would return. In publishing his findings in 1705, he wrote the confident and poignant words, "If it should return according to our predictions, impartial posterity will not refuse to acknowledge that this was first discovered by an Englishman." It was a quiet, humble, and yet incredibly bold statement. It was a declaration of faith in the power of scientific reason to understand and predict the workings of the cosmos. He had found the rhythm. He had understood the beat. And now all that was left was for humanity to wait and to listen for the next footfall of this great, silent visitor. Our journey to find the true home of Halley's comet has thus far taken us along its great elliptical path, to its lonely aphelion beyond the orbit of Neptune. Now we must venture further still, into a region of space that was, for most of human history, entirely unknown and unimagined. This is the third great zone of our solar system, a vast and icy frontier that lies beyond the realm of the giant planets. This region is known as the Kuiper Belt. For centuries, our map of the solar system ended with the planets. They were the known world, the entirety of the Sun's family. But in the 20th century, astronomers began to suspect that this map was incomplete. The discovery of Pluto in 1930 was the first clue. It was a small, icy world in a strange, tilted orbit, unlike any of the other planets. It seemed to be a resident of a new, undiscovered region of the solar system. Then, astronomers like Gerard Kuiper began to theorize that the solar system did not simply end after Neptune. They reasoned that in the primordial cloud of gas and dust from which the planets formed, the material in these distant, cold regions would have been too sparse to clump together into large planets. Instead, it should have formed a vast belt of countless small, icy bodies, leftovers from the creation of the solar system. This was a beautiful and logical theory, but for decades it remained just that, a theory. The objects in this hypothetical belt would be incredibly small, dark, and far away, making them almost impossible to detect with the telescopes of the time. It was not until 1992 that the first of these objects, other than Pluto, was finally discovered. This discovery opened the floodgates. In the years since, we have found thousands of these small, icy worlds, confirming that the Kuiper Belt is very much real. The Kuiper Belt can be imagined as a vast celestial debris field, a second asteroid belt, but far larger and made of ice instead of rock. It is a donut-shaped ring of material that begins just beyond the orbit of Neptune, at about 30 astronomical units from the Sun, and stretches out to about 50 astronomical units. It is a realm of profound cold and darkness, populated by millions of frozen bodies, ranging in size from small chunks of ice to dwarf planets like Pluto, Makemake and Haumea. These are the most primitive objects in our solar system, ancient time capsules that have remained almost entirely unchanged since their formation 4.5 billion years ago. They are the building blocks of planets that never were, a silent testament to the conditions of the early solar nebula. Understanding this distant frontier is the next crucial step in our journey to find the source of the celestial visitor that graces our own skies. Let us linger for a moment in this distant twilight realm and try to form a clearer picture of the Kuiper Belt. It is not an empty space with a few scattered objects, but a vast and richly populated structure, a great ring of icy worlds encircling the planetary part of our solar system. Thinking of it as a donut shape is a helpful analogy. It is a thick, flattened disk, generally aligned with the same plane in which the planets orbit, a plane we call the ecliptic. The inner edge of this ring is sharply defined by the orbit of the planet Neptune. Neptune's powerful gravity acts as a gatekeeper, sculpting the inner boundary of the belt and influencing the orbits of the objects within it. The belt then extends outward, a sprawling field of primordial debris, to a distance of about 50 astronomical units. Beyond this point, the population of objects seems to drop off quite sharply, in a feature that astronomers call the Kuiper Cliff. The reason for this sudden edge is still a gentle mystery, a quiet question that scientists are patiently trying to answer. The residents of this icy ring are known as Kuiper Belt objects, or KBOs. They are not packed closely together. The Kuiper Belt is a region of immense emptiness. The distances between these small worlds are vast. But in terms of population, it is a crowded neighborhood. Astronomers estimate that there are hundreds of thousands of KBOs larger than 100 kilometers, or 60 miles across, and likely millions of smaller, comet-sized bodies. These objects are composed primarily of frozen volatiles, the ices of water, methane, ammonia, and nitrogen, mixed with rock and dark organic compounds. They are in essence very similar in composition to the nucleus of Halley's comet. Among these countless smaller bodies are some of the most fascinating worlds in our solar system, the dwarf planets. Pluto is the most famous resident of the Kuiper Belt. Its discovery was the first hint of this region's existence, and we now understand it not as a lone misfit planet, but as the king of a vast population of similar icy worlds. Other dwarf planets like Haumea, which is shaped like a flattened egg and spins incredibly fast, and Make, another large and bright KBO, also call this region home. The presence of these large bodies tells us that even in this distant, cold region, some objects were able to grow to a significant size, though none ever became large enough to dominate their orbits and achieve the status of a full planet. This ring of icy worlds is a place of incredible stability. The objects here are on very slow, stable orbits, and they have likely been circling the Sun in this region, largely undisturbed, for billions of years. It is a cosmic museum, a place where the pristine building materials of the outer solar system have been kept in a deep freeze, waiting to be studied. It is a quiet, peaceful, and profoundly ancient place, a silent monument to the dawn of our solar system. This vast, icy ring of worlds we have been exploring, the Kuiper Belt, is not just a static museum of primordial objects. It is also a living, active source of some of the most beautiful visitors to our night sky. It is now understood to be the birthplace, the home reservoir, for a major class of comets, the short-period comets. Short-period comets are defined as those that take less than 200 years to orbit the Sun. For a long time, their origin was a puzzle. They seemed to come from a region that was closer and more orderly than the source of the long-period comets. The discovery of the Kuiper Belt provided the perfect answer. Here was a vast population of comet-sized icy bodies, orbiting in the same general plane as the planets, in a region just beyond Neptune. It was a ready-made source for these comets. The process by which a Kuiper Belt object becomes an active comet is a story of gentle gravitational nudges playing out over millions of years. The objects in the Kuiper Belt are on relatively stable circular orbits. However, their orbits can be slowly disturbed. Sometimes, two KBOs might pass close to each other, their mutual gravity altering their paths. More significantly, the immense gravity of the planet Neptune is constantly, subtly tugging on the objects in the inner parts of the belt. Over a very long time, these gravitational perturbations can be enough to push a KBO out of its stable, circular orbit and onto a new, more elliptical path. This new path might bring it close to Neptune itself. If that happens, the KBO can have a powerful gravitational encounter with the giant planet. Neptune's gravity can act like a cosmic slingshot, flinging the object inward onto a new orbit that takes it deep into the inner solar system. It is at this moment that a dormant Kuiper Belt object is transformed into what we call a centaur, a small body with an unstable orbit between Jupiter and Neptune. From there, further gravitational interactions with the other giant planets, especially Jupiter, can hand it down into the inner solar system, where it finally becomes an active, short-period comet. These comets, often called Jupiter family comets, are distinct. Their orbits are typically not very tilted with respect to the planets' orbits, and they travel in the same direction around the Sun as the planets do. They are the younger comets, in a dynamical sense. Their journeys into the inner solar system are relatively recent, and they have not been traveling this path for as long as some other comets. The Kuiper Belt, this distant, icy frontier, is therefore a place of quiet beginnings, a celestial nursery where dormant worlds wait for the gentle push that will begin their long transformation into the beautiful, transient visitors of light that we call comets. With the discovery of the Kuiper Belt as the source of short-period comets, it seemed for a time that the mystery of Halley's Comet's origin was solved. After all, with its 76-year orbit, it fits the definition of a short-period comet perfectly. It was natural to assume that it was simply the most famous member of this family, a large and active comet that had been nudged inward from this great icy ring beyond Neptune. However, the more closely astronomers studied Halley's unique path, the more they realized it didn't quite fit in. It carried with it a whisker of a clue, a subtle but profound difference that hinted at a much older and more distant story. The clue lies in the nature of its orbit. The comets that originate from the Kuiper Belt, the Jupiter family comets, tend to have orbits that are relatively well behaved. They orbit in the same direction as the planets, and their paths are not tilted at very steep angles to the ecliptic plane, the plane in which the Earth and most of the planets orbit. This makes sense, as they come from a flattened, donut-shaped belt that shares this same general orientation. Halley's Comet, however, breaks these rules. Its orbit is highly inclined, tilted at a dramatic angle of about 162 degrees to the ecliptic plane. This means it travels in what is called a retrograde orbit. It moves around the Sun in the opposite direction to the planets. If you were to look down on the solar system from above, you would see all the planets and the Kuiper Belt comets moving in a serene, counterclockwise direction. But Halley's Comet would be a rebel, moving clockwise against the flow of traffic. This is a very significant clue. It is very difficult to explain how a gentle nudge from Neptune or a collision within the Kuiper Belt could take a well-behaved object from that region and fling it with thickening into such a bizarre backward orbit. The dynamics just don't work easily. The orbit of Halley's Comet does not look like the orbit of an object that was born in the relatively flat, orderly system of the Kuiper Belt. Instead, its orbit looks much more like that of a different class of objects, the long-period comets. These comets, as we have briefly discussed, come from all directions in the sky, from a great spherical cloud, and can have orbits at any inclination, including retrograde ones. This whisker of a clue, the retrograde, highly inclined orbit, was the first strong indication that Halley's Comet was an imposter in the family of short-period comets. While it may be currently masquerading as one, its true origins, its ancient birthplace, must lie somewhere else, in a place that can produce comets with such wild and untamed orbits. This realization created a soft narrative turn in our quest, forcing us to look beyond the Kuiper Belt and to consider that our journey to find the comet's real home was not yet over. The strange retrograde orbit of Halley's Comet, that beautiful and telling clue, serves as a gentle but firm signpost, pointing us away from the Kuiper Belt and toward a more distant, more mysterious horizon. It tells us that to truly understand the origin of this most famous of comets, we must look further. Our visit to the Kuiper Belt has been essential. We have discovered a magnificent and vital part of our solar system, the home of dwarf planets and the birthplace of the Jupiter family comets. But it is not the final destination on our journey. It is a stepping stone, a crucial piece of the puzzle that by its very nature shows us where Halley's Comet does not come from. The Kuiper Belt is a place of relative order. It is a disk, a flattened structure that retains the memory of the spinning protoplanetary nebula from which the solar system was born. The comets that originate there carry this signature of order with them, orbiting on prograde, low-inclination paths. Halley's Comet, with its wild backward trajectory, carries the signature of chaos, or rather, of a different kind of order. the order of a great spherical system where orbits can exist at any angle in any direction. This forces us to re-evaluate our understanding of the comet. It is what astronomers call a Halley-type comet, a special category for objects that have the short periods of Kuiper belt comets but the orbital characteristics of long-period comets. This suggests a two-step origin story. It did not begin its life in the Kuiper belt. It began its life much, much farther away, in a place where retrograde orbits are common. It was born as a long-period comet. Then, on one of its passages through the solar system, it had a chance encounter with a giant planet, most likely Jupiter, which captured it, shrinking its enormous orbit into the 76-year loop we see today. Halley is a captured visitor from a much more remote realm. So, our journey of inquiry must now take a great leap outward. We must travel in our minds far beyond the Kuiper belt, past its mysterious outer edge and into the vast, empty gulf that separates our solar system from the nearest stars. We are in search of that great spherical shell of comets that was first theorized by Jan Oort. We are looking for the primordial cloud, the ancient cold reservoir that is believed to be the true birthplace of not just the long-period comets, but of Halley itself. This need to look further is a beautiful example of how science works. It is a process of gentle refinement, of finding an answer that then leads to a deeper question. The discovery of the Kuiper belt was a monumental achievement, but it did not solve everything. The universe is always more subtle and more wonderful than our initial theories. As we prepare to leave the Kuiper belt behind, we do so with a new sense of purpose, guided by the quiet clue of the comet's orbit. We are heading to the very edge of the sun's dominion, to the final and most profound destination of our journey. Our journey now takes us on its final and most profound leap, far beyond the familiar confines of the planetary system, past the icy ring of the Kuiper belt, and into the vast, dark expanse of interstellar space. We are traveling to the very edge of the sun's dominion, to a place so remote that it is not a ring or a belt but a great, all-encompassing sphere. This is the Oort cloud, the theoretical, ghostly shell of icy bodies that is believed to be the true, ancient home of Halley's comet. The Oort cloud is not a place we have ever seen directly. It is too far, and its inhabitants are too small, dark, and widely spaced to be imaged by even our most powerful telescopes. Its existence was first proposed in 1950 by the Dutch astronomer Jan Oort, who was trying to solve the puzzle of the long-period comets. He noticed that these comets, with orbits lasting thousands or millions of years, seemed to come from immense distances, and they arrived from all directions in the sky with equal likelihood. This suggested their source was not a flat disk, but a huge spherical cloud surrounding the entire solar system. The scale of the Oort cloud is difficult to comprehend. Its inner edge is thought to begin perhaps 2,000 to 5,000 astronomical units from the Sun, nearly 100 times farther out than Neptune. From there, it extends outward to a staggering distance of 50,000, or perhaps even 100,000 astronomical units. At its farthest extent, the Oort cloud reaches nearly a quarter of the way to the nearest star, Proxima Centauri. This is the true boundary of our solar system, the place where the Sun's gravitational influence finally gives way to the pull of the other stars and the galaxy itself. Objects in the Oort cloud are only very loosely bound to the Sun. They drift in immense, slow orbits that can take millions of years to complete. Here, at the edge of the Sun's dominion, they are susceptible to outside influences. The gentle gravitational pull of a passing star millions of years ago, or the tidal forces of the Milky Way galaxy itself, can be enough to disturb their peaceful orbits. It is these gentle nudges that are believed to be responsible for sending some of these icy bodies on their long, slow fall toward the inner solar system, where they become the long-period comets we see. To imagine the Oort cloud is to imagine a place of ultimate quiet and stillness. It is a realm of near-perfect darkness and absolute cold. The Sun is just a very bright star, its warmth completely absent. The planets are invisibly small, huddled together in the distant center. This great spherical shell is the final frontier of our solar system, a ghostly and beautiful structure that marks the edge of our Sun's family. It is from this immense, dark and mysterious place that the journey of Halley's comet, so very long ago, is believed to have begun. It is a messenger from the true edge, a visitor from a realm that we can only explore with the quiet power of our imagination and the gentle guidance of scientific thought. Having arrived at the conceptual shores of the Oort cloud, let us try to visualize this immense and ghostly structure. It is not a cloud in the earthly sense, not a dense fog of material. It is a sphere of almost perfect emptiness, populated by a vast number of small, icy worlds. The defining characteristic of the Oort cloud is its sheer scale and the profound solitude of its inhabitants. It is a structure defined more by the space it occupies than by the matter it contains. The Oort cloud is thought to be home to not millions, not billions, but potentially trillions of cometary nuclei. The total mass of all these objects is uncertain, but it is estimated to be several times the mass of the Earth, all spread out through a truly colossal volume of space. Despite this huge number of objects, the distances between them are astronomical. A typical Oort cloud comet would be tens of millions of kilometers away from its nearest neighbor. From the surface of one of these icy bodies, the sky would look completely black. You would not see any other members of the cloud. You would only see the distant stars and the pinprick of light that is our sun. This great sphere is believed to have two distinct parts. There is a vast, spherical outer Oort cloud, which extends to the very edge of the sun's gravitational influence. This is the region from which the long-period comets we observe are thought to originate, as it is the most susceptible to gravitational disturbances from passing stars. But there is also thought to be a denser, donut-shaped inner region, sometimes called the Hills cloud, which lies closer to the sun. This inner cloud is more tightly bound and may serve as a reservoir to replenish the outer cloud over billions of years. The objects within this sphere are on a wide variety of orbits. Unlike the planets and the Kuiper belt, which share a common orbital plane, the Oort cloud is isotropic. Its objects travel on paths with every possible inclination, coming from over, under, and all sides of the solar system. This is why long-period comets can appear from any point in our sky. They are not confined to the narrow band of the zodiac where we see the planets. Visualizing the Oort cloud is an exercise in contemplating immense, quiet emptiness. Imagine our entire planetary system, out to the edge of the Kuiper belt, as a tiny seed in the center of a vast invisible bubble. This bubble is the Oort cloud. It is a silent, cold, and dark sphere, a ghostly halo of 1 trillion sleeping comets, all patiently orbiting the distant sun, waiting for a gentle nudge to begin a journey that might one day bring them into our sky as a fleeting spectacle of light. It is the great unseen treasury of our solar system, a repository of its most ancient and pristine materials. The existence of this vast spherical cloud of 1 trillion comets raises a gentle but profound question. Where did all of these objects come from? How did this immense structure form at the very edge of our solar system? The answer takes us back to the very beginning, to the birth of the sun and planets. For the Oort cloud is not a foreign entity, but is made of the very same material as our own world. It is composed of the leftovers of creation. 4.5 billion years ago, our solar system was a vast spinning cloud of gas and dust, a protoplanetary disk surrounding a young, newly formed sun. In the inner part of this disk, where it was warmer, rocky materials condensed and began to clump together, forming the terrestrial planets, Mercury, Venus, Earth, and Mars. In the outer regions, beyond a boundary known as the frost line, it was cold enough for volatile compounds like water, ammonia, and methane to freeze into solid ice. This is where the great gas and ice giants Jupiter, Saturn, Uranus, and Neptune were born. Along with these giant planets, a huge number of smaller, icy bodies also formed in this region. These objects, called planetesimals, were the building blocks of the giant planet's cores. There were far more of these icy planetesimals than could be incorporated into the planets themselves. What happened to the rest of them is the story of the Oort cloud's origin. In the chaotic early days of the solar system, the giant planets, particularly the immense Jupiter and Saturn, migrated and shifted in their orbits. As they moved, their powerful gravity acted like a great cosmic slingshot, interacting with the countless smaller icy planetesimals around them. Many of these icy bodies were flung deep into the inner solar system, some to collide with the young Earth, perhaps delivering the water and organic molecules that would become crucial for life. Many others were ejected from the solar system entirely, sent hurtling into interstellar space, never to return. But a vast number of them were flung outward, not with enough energy to escape the sun's gravity completely, but into huge, highly elongated and unstable orbits. These objects formed a scattered, messy cloud of debris. Over hundreds of millions of years, the gentle, persistent gravitational tugs from the rest of the Milky Way galaxy and from occasionally passing stars worked to shape this cloud. These subtle, external forces acted to lift the orbits of these icy bodies out of the flat plane of the solar system and randomize their inclinations, eventually sculpting the chaotic, scattered cloud into the vast, stable, spherical shape of the Oort cloud we theorize today. The Oort cloud, therefore, is not made of objects that formed at the edge of the solar system. It is made of objects that formed much closer in the same neighborhood as the giant planets, and were then exiled to the solar system's most distant frontier. They are the primordial leftovers, the scattered remnants of our own creation story. Having understood its origin, let us return in our imagination to the Oort cloud as it exists today. It is, above all else, a realm of profound and almost perfect stillness. In the inner solar system there is constant activity. The solar wind streams outward, planets turn, moons orbit, and asteroids collide. But out here, in this distant spherical shell, all of that is an incredibly remote memory. The defining characteristic of the Oort cloud is its state of near-perfect preservation, a deep cosmic quiet that has persisted for billions of years. The stillness comes from the immense cold. At such a great distance from the sun, the temperature is just a few degrees above absolute zero. In this environment, the volatile ices that make up the cometary nuclei are frozen solid, as hard as rock. There is no sublimation, no outgassing, no activity of any kind. The comets are in a state of deep hibernation, their chemical and physical structure locked in place. The ancient materials from the dawn of the solar system, the water ice and organic molecules, are preserved in a pristine state, untouched by the heat and radiation that have so altered the objects of the inner solar system. The stillness also comes from the profound emptiness. With tens of millions of kilometers separating each object from its nearest neighbor, collisions are incredibly rare, perhaps occurring only once in the entire lifetime of the solar system. The comets do not interact with each other. They move on their vast, slow, independent orbits, each one an island of solitude in an ocean of dark space. There is no weather, no atmosphere, no geology. There is only the silent, patient passage of eons. This realm of stillness is the reason why the Oort cloud is so scientifically important. It is a perfect sample of the original solar nebula, frozen in time. When a gravitational nudge sends one of its residents on a journey inward, it becomes a messenger, a pristine probe sent from the earliest moments of our solar system's history. When we study the composition of a long-period comet, we are not just looking at a beautiful object, we are analyzing a piece of the past, a chemical fossil that tells us about the conditions in which our own world was born. This profound stillness is the natural state of a comet. The active, brilliant object we see in our sky is the exception, a brief and fleeting departure from its true nature. Its home is this quiet, cold and unchanging realm. Its life is one of silent, patient waiting in the dark. The journey inward is a violent and beautiful interruption, but the Oort cloud is the peaceful baseline to which it belongs, a place where time itself seems to move at a different, slower, and more graceful pace. We have now journeyed to the farthest reaches of our solar system, to the great spherical shell of the Oort cloud. We have explored its immense scale, its origins in the chaos of the early solar system, and its profound, quiet stillness. And it is here, in this remote and mysterious realm, that we find the definitive answer to our central question. The Oort cloud is the true birthplace of Halley's Comet. As we discovered when we examined the whisker of a clue in its orbit, Halley's Comet does not behave like a native of the Kuiper Belt. Its retrograde, highly inclined path is the signature of an object from a spherical, isotropic source. a source where orbits are not confined to the flat plane of the planets. The Oort cloud is the only such source we know of in our solar system. Therefore, the story of Halley must begin here. For billions of years, the object that would one day bear Edmund Halley's name was just one of the trillions of other dormant, icy nuclei, drifting silently through the cold and the dark. It was a long-period comet in waiting, circling the Sun on a vast, slow orbit that likely took millions of years to complete. It was an anonymous resident of this great celestial sphere, its existence completely unknown and unknowable to the inhabitants of the small, rocky world so much closer to the Sun. Then, at some point in the distant past, perhaps hundreds of thousands of years ago, something changed. A gentle gravitational disturbance, a nudge that we will explore in our next chapter, altered its immense, stable orbit. This nudge was just enough to send it on a new path, a long, plunging fall toward the inner solar system. For the first time, this anonymous piece of ice and dust journeyed into the realm of the planets. It became a long-period comet, a spectacular visitor from the deep freeze. It may have made several such passages, each one taking thousands or millions of years, its orbit slowly evolving with each trip. Then, on one of these passages, it had a fateful encounter. It passed close enough to one of the giant planets, likely Jupiter, that its orbit was dramatically changed. The planet's powerful gravity captured it, robbing it of the immense orbital energy that carried it out to the Oort cloud. Its aphelion was drastically reduced, and it was forced into a new, much smaller, and much shorter elliptical path. It was at this moment that Halley's comet was born, dynamically speaking. It was transformed from a long-period comet from the Oort cloud into the short-period 76-year visitor that we know today. It is a captured citizen, an immigrant from the solar system's most distant province. Its heart, its composition, its very essence is that of the Oort cloud. It is made of the pristine primordial material from the edge of the Sun's dominion. But its path, its life cycle, is now confined to the inner planetary part of the solar system. It is a messenger that has been convinced to stay, a wild visitor from the great spherical shell that has been tamed, for a time, by the gravity of the planets. This is its beautiful and complex story, a tale of two homes, the ancient, distant birthplace where its journey began, and the new, smaller orbit it now calls home. We have identified the Oort cloud as the comet's true home, a realm of profound stillness where a trillion icy bodies drift in stable, ancient orbits. This then leads to our next gentle question: what could possibly disturb such a peaceful existence? How does an object, after billions of years of quiet hibernation, begin the long fall inward that transforms it into a spectacular comet? The answer is not a violent collision or a dramatic explosion, but a subtle and patient process, a nudge from the great galactic neighborhood in which our solar system resides. The comets in the Oort cloud are at the very edge of the Sun's gravitational influence. They are held in a delicate balance. The Sun's pull is just strong enough to keep them from drifting away into interstellar space, but it is weak enough that they are susceptible to other, very subtle gravitational forces. These forces are the architects of the comet's journey, the unseen hands that select one dormant nucleus out of trillions and send it on its way. One of the most significant of these forces is the influence of passing stars. Our Sun is not fixed in space. It is orbiting the center of the Milky Way galaxy, and as it does, other stars occasionally pass by. These encounters are not close in any human sense. A passing star might come within a light year or two of our solar system, but even at this immense distance, the star's gravity can be strong enough to perturb the fragile orbits of the comets in the outer Oort cloud. As the star passes, its gravitational field creates a slow, gentle ripple through the cloud, subtly changing the speed and direction of the comets it passes near. For most comets, this nudge might simply shift them into a slightly different, but still stable, Oort cloud orbit. But for a few, the nudge might be just right to cancel out some of their orbital momentum, causing them to lose the energy that was holding them up against the Sun's gravity. With this energy gone, they have no choice but to begin to fall inward. Another powerful influence is the galactic tide. Just as the moon's gravity creates tides in Earth's oceans, the combined gravity of the billions of stars in the Milky Way's disk creates a subtle tidal force that stretches and squeezes the Oort cloud. This constant, gentle force can, over millions of years, slowly deform the orbits of comets, gradually changing their shape until one is pushed onto a path that takes it toward the sun. This process is incredibly slow and patient. The nudge does not send the comet hurtling inward. It simply places it on a new path, a path of falling. The journey from the Oort cloud to the inner solar system can take millions of years. The comet starts to move at an incredibly slow pace, gradually accelerating as it gets closer to the sun. It is a long, lonely and silent fall from the darkness into the light. And it is this process, this gentle cosmic push, that is the ultimate origin of the long-period comets we see, and the event that began Halley's own story so very long ago. It is a beautiful reminder that our solar system is not an isolated island, but is connected to the great, breathing, gravitational ecosystem of the galaxy around it. To truly appreciate how a gentle nudge can begin such a grand journey, we must first understand the state of existence for a comet in the Oort cloud. It is a life lived on a knife's edge of gravitational balance. The comet is in a constant, delicate dance between two immense and opposing forces: the inward pull of its parent star, our Sun, and the subtle, collective pull of the entire Milky Way galaxy that surrounds it. For millions, even billions of years, these forces can exist in a state of near-perfect equilibrium, allowing the comet to maintain its vast, stable orbit in the cold and the dark. The Sun's gravity, though weakened by immense distance, is the primary force that defines the comet's orbit. It is what makes the comet a member of our solar system, tethering it to its origin. This pull is what creates the comet's path, a slow million-year loop around a star it can barely see. It is a familiar, constant presence in the comet's existence, the anchor of its cosmic home. But unlike the planets, which are deep within the Sun's gravitational well and almost entirely immune to outside influences, the comets of the Oort cloud are in a much more precarious position. They are at the frontier, the borderland where the Sun's dominion begins to fade. Out here, other gravitational voices begin to be heard. The most significant of these is the galactic tide. This is not the pull of any single object, but the integrated gravitational field of the entire galaxy. The disk of the Milky Way, with its billions of stars, gas and dark matter, exerts a gentle but persistent tidal force that stretches the Oort cloud, subtly shaping it and the orbits of everything within it. This galactic tide creates a constant low-level stress on the orbits of the Oort cloud comets. It is a quiet background hum of gravity that is always present. For an orbit to remain stable for eons, it must exist in a state of harmony with this tidal force. The slightest imbalance, the smallest deviation, can be magnified over millions of years, slowly changing the shape and orientation of the comet's path. This delicate balance is the key. The comet is not held in a rigid, unchangeable orbit. It is in a dynamic, fluid state of equilibrium. It is like a leaf floating on the surface of a perfectly still pond, where the slightest breeze can set it in motion. The comet's vast orbital energy is almost perfectly balanced by the Sun's gravitational potential energy. It has just enough speed to keep from falling in, but not enough to escape. It is this state of perfect, fragile balance that makes the Oort cloud such a sensitive and responsive structure, a place where the whisper of a passing star can be enough to shatter the stillness and initiate a journey of a million years. Our Sun and its distant family of comets are not alone in the galaxy. They are part of a great, swirling river of stars, all orbiting the galactic center. As we travel, we are constantly, slowly, moving through a neighborhood of other stellar systems. On occasion, another star will pass relatively close to our own. This is not a dramatic near-collision event. In the vastness of interstellar space, close can still mean a light year or more away, trillions of kilometers of empty space separating the two stars. Yet, even at this immense distance, the passing star's gravity can reach across the void and gently touch the delicate orbits of the comets in our Oort cloud. Imagine our solar system, with the Oort cloud as its great spherical halo moving silently through the galaxy. Now, imagine another star, perhaps a small, dim red dwarf or a star much like our own sun on its own path through the galaxy. For thousands of years, this star would be an unremarkable point of light in the sky. It would gradually grow brighter as it approached, and then it would begin to dim as it receded, its passage taking hundreds of thousands of years to complete. To any observer in the inner solar system, the event would be almost entirely unnoticeable. The passing star would likely never even become one of the brightest stars in our night sky. But for the comets in the Oort cloud, this silent passage is a significant event. As the visiting star glides by, its gravitational field moves through the outer regions of the Oort cloud. The comets in that part of the cloud feel its pull. They are gently tugged in the direction of the passing star. This is not a sudden, sharp pull, but a slow, persistent acceleration that lasts for thousands of years as the star makes its closest approach and then moves away. This encounter is a purely gravitational conversation between two stellar systems. There is no exchange of matter, no flash of light, just the silent, invisible interaction of their masses. The passing star is like a great ship moving through still water, leaving a slow, gentle wake behind it. The comets of the Oort cloud are like tiny boats floating in that water, and as the wake reaches them, they are lifted and shifted, their quiet equilibrium disturbed. This event, a star passing through the sun's distant neighborhood, is thought to be the most common and most effective mechanism for dislodging comets from their stable orbits and starting them on their journey toward the inner solar system. It is a beautiful illustration of the interconnectedness of the galaxy, a reminder that even in the vast emptiness, no star is truly an island. The gravitational influence of the passing star does not act like a hand, picking one specific comet and throwing it toward the sun. Instead, it creates a subtle, widespread disturbance, a cosmic ripple that propagates slowly through the vast, fragile structure of the Oort cloud. This ripple is a wave of gravitational potential, a gentle warping of space-time that alters the energy and momentum of every comet it touches. As the star passes, its gravity adds a tiny amount of energy to the orbits of the comets on the side of the Oort cloud it is approaching, and it removes a tiny amount of energy from the orbits of the comets on the side it is leaving behind. It is this removal of energy that is the key. An orbit is a delicate balance between an object's forward momentum, its kinetic energy, and the inward pull of gravity, its potential energy. To send a comet falling toward the sun, you need to reduce its kinetic energy to slow it down in its orbit just enough for gravity to win. The cosmic ripple from the passing star does exactly this. For a comet in just the right position, the gentle, persistent tug from the star, as it recedes, is in the perfect direction to act as a brake, slowing the comet's motion. The change in velocity is minuscule, perhaps only a few meters per second, a change that would be completely insignificant for a planet in the inner solar system. But for a comet in the Oort cloud, living on the very edge of gravitational stability, this tiny change is catastrophic to its equilibrium. Its orbital speed now drops just below the threshold required to maintain its distant, stable path. The delicate balance is broken. The sun's gravity, which was previously held at bay by the comet's momentum, now becomes the dominant force. The comet has been nudged off its stable perch and onto a new, unstable trajectory. It has been placed at the top of a very long, very shallow gravitational hill, and it has no choice but to begin to roll down. This process is not selective. The ripple affects a vast region of the Oort cloud, nudging millions or even billions of comets at once. Most of these nudges will be insignificant, simply shifting a comet into a slightly different stable orbit. But statistically, a few of these comets will be perturbed in just the right way. Their orbital speeds reduced just enough to send them on the long fall inward. The cosmic ripple is a gentle, almost imperceptible event, but its consequences are profound. It is the trigger, the first domino in a chain of events that will, millions of years later, result in the appearance of a brilliant, unexpected visitor in the night sky of a world so very far away. The cosmic ripple has passed. The passing star has receded into the distance, and for one particular comet, everything has changed. Its orbit, once a stable million-year loop at the edge of the solar system, has been broken. It is now on a new path, a journey that will take it away from its cold, dark home and into a realm of light and warmth it has never known. This is the beginning of the long fall inward, a patient and silent journey that is the true first chapter in the life of an active comet. The fall does not begin with a dramatic plunge. It begins with an almost imperceptible movement. Having lost a tiny fraction of its orbital speed, the comet starts to yield to the sun's distant gravity. It begins to move inward, but at a pace that is incredibly slow. For centuries, for millennia, it would seem to hang almost motionless, its progress measured in inches per second. From its perspective, the sun would not appear to grow any larger, the stars would not shift. This is a journey that operates on a timescale that dwarfs human history. As it falls, it is also accelerating. But the acceleration is so gentle at first that it is almost meaningless. It is following the shallowest of gravitational gradients, slowly picking up speed as it gets drawn deeper into the sun's gravitational well. For thousands of years, it might travel through the outer Oort cloud, a silent, frozen object, its destiny now set, but its appearance utterly unchanged. As it continues to fall, its path takes the shape of a new, extremely elongated ellipse, or perhaps a parabola. Its aphelion, its farthest point, is now its starting point in the Oort cloud. Its perihelion, its closest point, is now somewhere deep within the inner solar system, a destination it will not reach for an immense amount of time. The journey may take anywhere from 1 to several million years to complete. During this time, the comet is utterly alone. It crosses the vast, empty gulf between the Oort cloud and the Kuiper belt, a journey of trillions of kilometers. It passes through the Kuiper belt, a ghost in a graveyard of other sleeping comets. It continues inward, finally crossing the orbit of Neptune, then Uranus, Saturn, and Jupiter. All the while, it is gathering speed. The gentle fall has now become a determined plunge. The sun is growing steadily brighter, its warmth beginning to touch the comet's surface for the first time in perhaps billions of years. This long, slow fall is a process of transformation. The comet is moving from one cosmic environment to another, from a place of perfect stability to a place of dynamic change. It is being delivered from the deep freeze of the solar system's attic to the fiery hearth of its center. By the time it reaches the inner solar system and begins to awaken, it is a truly ancient object, a primordial messenger that has spent millions of years on its silent, patient journey, all because of a single, gentle nudge from a passing star, an eternity ago. This story of a cosmic nudge and a long, slow fall is not just a general theory about comets. It is, we believe, the specific story of our comet. The ancient push that started Halley's comet on its very first journey toward the sun likely happened in the distant, unrecorded past, perhaps millions of years ago. A star, whose name we will never know and whose path is now lost to the great shuffle of the galaxy, drifted through the sun's neighborhood and sent a gentle, gravitational ripple through the Oort cloud. And one of the trillions of comets affected by that ripple was the one that would one day be named 1P Halley. That single ancient event was the origin of everything we have discussed tonight. It was the moment that this particular piece of primordial ice and dust was singled out, its destiny changed forever. It began its own long fall inward, a multi-million-year journey from the dark, cold periphery to the bright, warm center. It made its first spectacular passage through the inner solar system as a long-period comet, its tail stretching across the sky, a brilliant but anonymous visitor. It may have made several such passages, its orbit slightly altered each time by the pull of the giant planets. With each pass, it was playing a game of gravitational chance. Then, on one fateful trip, it passed just close enough to Jupiter, or perhaps one of the other gas giants, for its destiny to be changed once more. The planet's immense gravity acted as a powerful brake, capturing the comet and slinging it into a new, much smaller orbit. The ancient push from a passing star got it started, but it was the powerful pull of a planet that trapped it, turning it from a visitor with a million-year cycle into a resident with a 76-year one. This story beautifully illustrates the immense and patient timescales of the cosmos. The events that shape the comet we see today are ancient and slow. The original nudge happened in a time so remote that our own species did not yet exist. The capture into its current orbit may have happened tens or hundreds of thousands of years ago, still long before the dawn of recorded human history. The comet we see is the end product of a long and complex dynamical history, a history written in the language of subtle gravitational interactions. When we look up at Halley's comet in the sky, we are not just seeing an object, we are seeing the culmination of this ancient story. We are seeing a visitor from the Oort cloud whose journey was initiated by a passing star and then shaped by the planets. It is a testament to the fact that the solar system is not a static, unchanging place, but a dynamic and evolving system, where the gentle forces of gravity can, over eons, create beautiful and unexpected results. The ancient push is a reminder that the comet's journey did not begin 76 years ago, but in the deep, cosmic past, in a moment of quiet, gravitational poetry. The story of Halley's comet does not end when it fades from our view and journeys back into the outer solar system. It leaves a delicate and beautiful legacy behind, an invisible monument to its passage that remains in the inner solar system long after the comet itself is gone. With every fiery embrace of the sun, the comet sheds a small portion of its substance, leaving behind a trail of dust and debris in its wake. This material does not simply dissipate. It continues to orbit the sun, forming a vast, ghostly river of cosmic dust that traces the exact path of the comet's orbit. This river of debris is known as a meteoroid stream. It is composed of the tiny particles, most no larger than a grain of sand or a small pebble, that were lifted from the comet's nucleus by the sublimating gases. Once freed from the nucleus, these particles become, in effect, tiny little planets, each one on its own independent orbit around the sun. These orbits are not exactly the same as the comet's, but they are very, very similar. The gentle pressure of sunlight and slight differences in their ejection speed cause them to spread out over time, both ahead of and behind the comet, and to widen into a diffuse, tube-like cloud that encircles the entire orbit. So, even when Halley's comet is at its farthest point from the sun, hibernating in the cold beyond Neptune's orbit, its presence is still felt in our neighborhood. This vast, invisible structure, the Halley meteoroid stream, is a permanent feature of our solar system, a constant reminder of the comet's many journeys. The stream is denser in some parts than others, with the thickest concentrations of dust particles marking the paths of more recent passages. But the entire 76-year orbital loop is marked by this trail of shed material. This wake is a physical record of the comet's slow transformation. It is the tangible evidence of the comet's aging process, the material it has sacrificed to create its beautiful display of light. Each tiny dust grain in this stream is a pristine piece of the primordial solar system, a microscopic time capsule released from the comet's ancient, icy heart. The stream is not just dust. It is a library of information about the comet's composition, a scattered archive of its very essence. For most of the time, this great, invisible river flows through space unseen and unnoticed. It is a ghost of the comet, a silent testament to where it has been. But on occasion, our own planet Earth, on its own journey around the sun, happens to cross paths with this stream. And in those moments, the comet's wake is revealed to us in a beautiful and breathtaking display of celestial light. It is in these moments that we can have a direct and tangible connection with this famous visitor from the Oort cloud. Our planet Earth is also on a journey, a steady and reliable one-year orbit around the sun. For the most part, our path through the solar system is through a region of almost perfect emptiness. But the solar system is not entirely clean. It is filled with the dusty legacies of comets and the rocky debris of asteroids. And as it happens, the Earth's orbit, our path through space, intersects the vast invisible river of dust left behind by Halley's comet. And it does not do so just once, but twice every single year. This is a beautiful coincidence of celestial geometry. The great tilted elliptical path of Halley's comet passes through the flat, nearly circular plane of Earth's orbit at two specific points. One of these intersections occurs on the part of the comet's orbit where it is heading inward, toward the sun. The other occurs on the part of its orbit where it is heading back outward, toward the cold depths of space. Because the dust shed by the comet has spread out to fill its entire orbital path, This means that every year, like clockwork, the Earth flies through this stream of cometary debris. Imagine the comet's orbit as a giant tilted hula hoop, and the Earth's orbit as a smaller, flat plate. The hula hoop passes through the plate at 2 points on opposite sides. Every year, as the Earth makes its circuit, it passes through the first of these intersection points around early May. Then, 6 months later, it arrives at the second intersection point, on the other side of its orbit, around late October. When the Earth passes through one of these points, it is not a dramatic or dangerous event. The dust particles in the stream are incredibly tiny and are spread very far apart, but they are moving at immense speeds relative to the Earth. As our planet plunges through the stream, these tiny particles of cometary dust enter our atmosphere at velocities of over 100,000 miles per hour. At this incredible speed, the friction with the air molecules in our upper atmosphere is immense. The tiny dust grain is heated to incandescence in a fraction of a second, burning up in a brilliant, fiery streak of light. This streak of light is what we call a meteor or a shooting star. It is not a star at all, of course, but the final, fleeting moment of a tiny piece of Halley's Comet, ending its billions of years-long existence in a flash of light, some 60 miles above our heads. When the Earth passes through the Halley meteoroid stream, we are treated to a meteor shower, a time when we can see not just one or two shooting stars, but many, all seeming to radiate from a single point in the sky. It is in these moments that the invisible becomes visible, and the comet's wake reveals itself to us. The first of our annual encounters with the legacy of Halley's Comet occurs in late April and early May. This is when the Earth intersects the stream of debris that the comet leaves on its inbound journey toward the Sun. The resulting meteor shower is called the Eta Aquariids. It is one of the most beautiful and reliable meteor showers of the year, particularly for observers in the southern hemisphere. The shower gets its name from the point in the sky from which the meteors appear to radiate. This point, called the radiant, lies in the constellation Aquarius, near one of its brighter stars, Eta Aquarii. This is an effect of perspective, similar to how parallel railroad tracks appear to converge at a point in the distance. The dust particles are all traveling on parallel paths, and as they hit the Earth's atmosphere, they appear to be streaming away from this single point in the sky. To watch the Eta Aquariid meteor shower is to witness the ghost of Halley's Comet firsthand. The best time to look is in the hours before dawn, when the radiant in Aquarius has climbed high enough above the horizon to be seen clearly. You need no special equipment, just a comfortable place to lie back, away from city lights, and to let your eyes adapt to the darkness. As you watch, you will see them, quick, silent streaks of light, appearing and vanishing in an instant. The meteors of the Eta Aquariids are known for their speed. Because Halley's Comet orbits the Sun in a retrograde direction, opposite to the Earth, we are hitting its debris stream almost head-on. This results in very fast meteors, which enter our atmosphere at about 66 kilometers per second, or 150,000 miles per hour. Their great speed often means they leave behind persistent, glowing trails, incandescent paths of ionized air that can linger in the sky for a few seconds after the meteor itself has vanished. For those in the northern hemisphere, the radiant of the shower does not climb very high in the sky before dawn interferes. This means that viewers may see fewer meteors, but they are often treated to a special kind of meteor called an earthgrazer. These are meteors that come in at a very shallow angle and skim along the top of the atmosphere for a long distance, creating spectacular, long-lasting streaks that can travel halfway across the sky. Each one of these brief flashes of light is a direct physical connection to the comet. It is a tiny piece of its heart, a grain of dust that was once locked in the ice of its nucleus, now ending its journey in our own atmosphere. The Eta Aquariids are the first of the comet's 2 annual gifts to us, a beautiful, silent reminder in the warm nights of May that its presence lingers in our skies, even when it is a billion miles away. 6 months after our passage through the inbound trail of Halley's Comet, the Earth, having traveled to the other side of the Sun, encounters the comet's legacy once more. In mid to late October, our planet crosses the outbound part of the comet's orbit, the stream of debris it leaves behind as it journeys away from the Sun. This second encounter produces another magnificent meteor shower, the Orionids. Like its May counterpart, the Orionid meteor shower is named for the location of its radiant, the point in the sky from which the meteors appear to originate. For the Orionids, this point lies in the constellation Orion, the great hunter, one of the most recognizable and beloved constellations of the autumn and winter sky. The radiant is near Orion's mighty club, just north of its brightest star, the reddish Betelgeuse. This makes the shower particularly easy and rewarding to watch, as the meteors seem to stream away from one of the most beautiful backdrops in the heavens. The Orionids are, in essence, the twin sister of the Eta Aquariids. They are born from the very same parent, Halley's Comet, and the particles that create them are part of the same great meteoroid stream. Consequently, they share many of the same characteristics. The Orionid meteors are also known for their incredible speed, entering our atmosphere at the same blistering velocity as the Aquariids, a result of that same head-on collision between Earth's orbit and the comet's retrograde path. This great speed means that the Orionids are often very bright, and they are famous for producing fireballs, exceptionally brilliant meteors that can outshine the brightest stars. And like their siblings in May, they frequently leave behind persistent glowing trains, luminous echoes that hang in the air for a moment after the meteor has passed. On a clear, dark night, during the shower's peak around October 21st, an observer might be able to see 10 to 20 of these swift meteors every hour. The experience of watching the Orionids is a profound one. On a crisp autumn night, as you lie looking up at the familiar form of Orion, you are watching our world connect with the dust of a comet that is, at that moment, perhaps billions of miles away, coasting silently through the frigid darkness beyond Saturn. Each streak of light is another grain of primordial dust, another tiny piece of the ancient solar nebula, completing its long journey. The Orionids are the second of the comet's annual whispers, a beautiful reminder that its path and ours are forever intertwined. They are a celestial echo, a gift of light in the October night that connects us directly to the great, sleeping heart of Halley's Comet. The twin meteor showers, the Eta Aquariids in May and the Orionids in October, are more than just beautiful celestial events. They represent something deeper, a profound and tangible connection between our world and this distant icy traveler. They transform Halley's Comet from an abstract object, a point of light seen once in a lifetime, into something that we can experience directly, physically, and reliably, year after year. When you see a meteor streak across the sky, you are not just seeing light. You are witnessing a physical event, the immolation of a piece of matter. That matter, that tiny grain of dust, has traveled an almost unimaginable journey. It was born in the primordial solar nebula, 4.5 billion years ago. It was incorporated into the nucleus of Halley's Comet, a body that formed in the cold outer reaches of the solar system. It was then exiled, along with the rest of the Oort cloud, to the very edge of the sun's influence, where it remained in a deep freeze for eons. It began its long fall inward millions of years ago, and was then captured into its current 76-year orbit. On a recent pass by the sun, perhaps only a few hundred or a few thousand years ago, it was finally liberated from the nucleus, cast off into space to join the great meteoroid stream. And after all that, after a journey through space and time that is almost beyond our ability to comprehend, it ends its existence by colliding with the atmosphere of our planet, creating a momentary streak of light for you to see. This is a powerful and humbling thought. We cannot reach out and touch Halley's Comet itself, but twice a year, Halley's Comet reaches out and touches us. Its dust rains down upon our planet, a gentle, almost imperceptible seeming influx of cosmic material. Most of it burns up high in the atmosphere, but the very smallest particles can survive their fiery descent and eventually settle to the ground as microscopic dust. Every day, the Earth is dusted with the remnants of comets and asteroids, a constant, gentle reminder of our connection to the wider solar system. The meteor showers make this connection visible and personal. They are a shared human experience. When you watch the Orionids, you are participating in a celestial event that has been happening every October for thousands of years. ever since the comet first laid down its dusty trail. Your ancestors, looking up at the same constellation, saw the very same streaks of light, born from the same cosmic parent. This tangible connection fosters a sense of belonging. It reminds us that our planet is not an isolated system, but is an integral part of a much larger cosmic environment. We are traveling through a solar system that is filled with the stories and the legacies of objects like Halley's Comet. The dust in its wake is the dust of our own origins. By watching its remnants burn up in our sky, we are, in a very real sense, watching tiny pieces of our own history being written in light. The meteor showers are a beautiful recurring gift, a tangible link that transforms a distant comet into a familiar, intimate, and ever-present part of our world. For millennia, our relationship with Halley's Comet was that of a distant observer. We watched it from afar, first with fear, then with curiosity, and finally with scientific understanding. But for all our knowledge of its orbit and its history, the comet itself, the nucleus, the sleeping heart remained a mystery. A tiny point of light hidden within a vast, glowing coma. That all changed during its last visit to our neighborhood. The return of Halley's Comet in 1986 coincided with a remarkable new era in human history, the age of space exploration. For the first time, we were no longer bound to the surface of our planet. We could send robotic emissaries, extensions of our own senses, out into the solar system to meet these celestial visitors up close. The plan that formed was a beautiful example of international scientific cooperation. It was called the Halley Armada. An international fleet of spacecraft was prepared to intercept the comet as it passed through the inner solar system. 2 probes were sent by the Soviet Union, the Vega 1 and Vega 2. 2 more were sent by Japan, Sakigake and Suisei. But the most ambitious of these missions, the one that was designed to get closer than any other, was a mission from the European Space Agency. It was a small, drum-shaped spacecraft, a quiet and patient robotic explorer. And it was given a beautiful and fitting name, Giotto. The mission was named after the early Italian Renaissance painter Giotto di Bondone. As we have learned, it is believed that Giotto witnessed the comet's appearance in 1301, and was so inspired that he depicted it as the Star of Bethlehem in his fresco, The Adoration of the Magi. It was a name that beautifully linked the artistic and scientific quests to understand the comet, a bridge between the old world of wonder and the new world of exploration. The goal of the Giotto mission was simple in concept, but incredibly difficult in practice. It was to fly as close as possible to the comet's nucleus, and to capture the first ever detailed images of this mysterious object. It was an act of immense precision and daring. The spacecraft would have to travel for 8 months and hundreds of millions of miles to arrive at the right place at the right time to meet a target only a few kilometers across, all while that target was moving at a speed of nearly 70 kilometers per second. This was not a high-stakes race or a dramatic quest for glory. It was a quiet, patient, and meticulously planned expression of pure human curiosity. It was the culmination of centuries of looking up at the sky and wondering. Now finally we had the ability to go and see for ourselves. The Giotto mission represents humanity's reach, our gentle but determined effort to extend our understanding beyond the shores of our own world, and to come face to face with the ancient, silent visitors that have so long captivated our imagination. The journey of the Giotto spacecraft was a masterpiece of celestial navigation, a quiet and precise ballet danced across the inner solar system. Launched on an Ariane 1 rocket in July of 1985, the small probe was sent on an 8-month cruise through interplanetary space. Its path was carefully calculated to intercept Halley's Comet on the night of March 13, 1986, just a month after the comet had passed its closest point to the Sun, and was heading back out into the solar system. The mission was a collaborative effort. The 2 Soviet Vega probes were designed to fly by the comet a few days before Giotto. Their primary role was to act as pathfinders. They would fly through the outer parts of the coma, locate the nucleus precisely, and relay that information back to the European Space Agency's control center. This would allow the Giotto team to make last-minute adjustments to their spacecraft's trajectory, guiding it with incredible accuracy toward its target. It was a beautiful example of international cooperation. a shared quest for knowledge that transcended the political tensions of the time. As Giotto approached the comet, it was traveling at an immense relative speed. Because the comet moves in a retrograde orbit, opposite to the spacecraft, their combined closing speed was nearly 70 kilometers per second, or over 150,000 miles per hour. At this velocity, even a particle as small as a grain of sand could have a devastating impact, capable of disabling or destroying the probe. To protect itself, Giotto was equipped with a special dust shield, an innovative, multi-layered defense designed by the American astronomer Fred Whipple, the same man who had first proposed the dirty snowball model of comets. The shield consisted of a thin outer layer of aluminum and a thicker inner layer of Kevlar. The idea was that a dust particle would strike the first shield and be vaporized, and the resulting cloud of gas would then disperse over a wider area before hitting the second, stronger shield, thus protecting the delicate instruments behind it. In the final hours of its approach, the spacecraft was oriented so that its dust shield faced forward, its antenna was pointed toward Earth, and its small camera was peeking out from behind the shield, ready to begin its work. The scientists on Earth could only wait. They had done everything they could. The little probe was on its own now, a silent emissary from humanity, about to plunge into the heart of the great comet, on a mission to finally reveal the face of this familiar stranger. It was a journey of incredible technological audacity, but at its heart, it was a quiet, patient, and peaceful pilgrimage to meet an ancient visitor. In the final hours of its approach on March 13, 1986, the Giotto spacecraft began its historic passage into the glowing, ethereal atmosphere of Halley's comet, the Comet. This was the most perilous part of its journey, a high-speed transit through a vast cloud of gas and dust. The environment it was entering was unlike anything a spacecraft had ever encountered before. It was a realm of beauty and danger, a place where the comet's secrets were guarded by a storm of its own shed material. As Giotto flew deeper into the Comet, its instruments began to send back a stream of information. It could taste the chemical composition of the gases, confirming the presence of water, carbon monoxide, carbon dioxide, and other volatiles, just as predicted. But it also found something more, a rich variety of complex organic molecules, the carbon-based building blocks of life. For the first time, we had direct evidence that these pristine, ancient bodies carried the very ingredients that may have been essential for life to begin on Earth. The spacecraft's dust detectors began to register impacts. At first, there were just a few, the tiny pings of microscopic particles striking the protective shield. But as Giotto plunged deeper and closer to the nucleus, the frequency of impacts increased dramatically, rising to hundreds and then thousands per second. The spacecraft was flying through a blizzard of ancient dust, a testament to the incredible activity of the comet's heart. Through its camera, the view was mesmerizing. The Comet was not a uniform, fuzzy cloud. It was a dynamic, structured environment. Giotto's images revealed great jets of dust and gas, erupting from the unseen nucleus and stretching out for thousands of kilometers. The spacecraft was flying through these jets, being sandblasted by the very material that made the comet so beautiful from afar. The final minutes were the most intense. The constant barrage of dust particles was taking its toll. 14 seconds before its closest approach, a larger particle, perhaps the size of a grain of rice, struck the spacecraft. The impact was powerful enough to jolt Giotto, sending it into a gentle, tumbling spin. The orientation of its antenna shifted, and for a terrifying 32 minutes, communication with Earth was lost. The scientists in the control room could only hold their breath and wait, hoping their brave little probe had survived its closest encounter. Despite the damage, the mission had already been a breathtaking success. It had journeyed into the heart of the glowing cloud and had given us our first intimate portrait of the environment around a comet's nucleus. Just before that final jarring impact sent the spacecraft tumbling, the camera aboard Giotto achieved its primary objective. In the final seconds of its approach, it transmitted a series of images that were, for the first time in history, clear enough to reveal the solid, sleeping heart of the comet. After millennia of seeing Halley's comet as a fuzzy, ethereal light in the sky, humanity was finally looking upon its true face. The moment was one of quiet, profound revelation. The images that came back were astonishing. The nucleus was not the bright, reflective snowball that many had imagined. Instead, it was dark. Incredibly dark. The surface was pitch black, one of the least reflective objects ever observed in the solar system, reflecting only about 4% of the light that struck it, darker than a lump of coal. This confirmed what some theories had suggested, that the repeated sublimation of ices leaves behind a crust of dark, carbon-rich dust and organic material that coats the surface. The dirty snowball was perhaps more of a snowy dirtball. The shape was also a surprise. The nucleus was not a sphere, but a highly irregular, elongated body, about 15 kilometers long by 8 kilometers wide. Its shape was often likened to that of a peanut or an avocado. The surface was not smooth, but rough and textured, showing evidence of hills, valleys, and perhaps crater-like depressions. It was a real, tangible world, with its own unique geography, sculpted by eons of slow erosion in the sun's heat. But the most breathtaking feature revealed in the images was the activity. The dark surface was not uniformly dormant. From several specific, localized regions on the sunlit side of the nucleus, brilliant, powerful jets of gas and dust were erupting into space. The images showed that only a small fraction of the surface, perhaps 10%, was active. The rest was covered by the inert, protective crust. The comet was not like a pot of water boiling all over. It was more like a geyser, with activity bursting forth from a few distinct vents. These jets were the source of the entire coma and the magnificent tails. For the first time, we could see the engine of the comet at work, the direct link between the solid nucleus and the vast, glowing spectacle it produced. Even after communication was lost, the mission was a triumph. The probe had survived its passage, flying within just under 600 kilometers of the nucleus. And though its camera was damaged, many of its other instruments were still functioning. Giotto had pulled back the curtain. It had transformed the comet from a point of light into a place, a complex and dynamic world with a unique character and a story to tell. The quiet revelation from those few, precious images completely revolutionized our understanding of comets, providing the ground truth that all future theories would be built upon. It was a beautiful, fleeting, and unforgettable first look. The Giotto mission, though its close encounter with Halley's comet lasted only a few brief, frantic minutes, left behind a legacy of knowledge that continues to shape our understanding of the cosmos. Its journey was more than just a successful engineering feat. It was a pivotal moment in the history of planetary science, a mission that transformed comets from celestial phantoms into real, tangible objects of study. Before Giotto, our knowledge of comets was based entirely on remote observation. We could analyze the light from their comas and tails to infer their chemical composition, and we could track their orbits to understand their paths. Fred Whipple's dirty snowball model was a brilliant piece of theoretical work, but it was still just a model. Giotto provided the first ground truth, the first direct, close-up observations that could confirm, deny, and refine our theories. The mission's most immediate legacy was the confirmation that comets do indeed have solid, single nuclei. It showed us the true nature of this nucleus, its irregular shape, its dark, dusty surface, and its localized, jet-like activity. This fundamentally changed our mental image of a comet. It was no longer an abstract concept but a specific type of world, with its own unique and complex processes. The discovery of the dark surface, for example, explained why comets could absorb so much solar energy and become so active, even at great distances from the sun. Giotto's analysis of the dust and gas in the coma also provided a wealth of new information. It gave us the first detailed inventory of the chemical ingredients in a comet, confirming that water is the dominant ice, but also revealing the surprising abundance and complexity of organic molecules. This finding had profound implications for our understanding of our own origins, lending strong support to the idea that comets could have seeded the early Earth with the chemical building blocks necessary for life. The survival of the Giotto spacecraft itself was a testament to the innovative design of its dust shield and gave engineers valuable data for designing future missions to comets and asteroids. In fact, Giotto's story did not end at Halley. The spacecraft, though damaged, was put into a long hibernation. Years later, it was reawakened and successfully redirected to fly by a second, much fainter comet named Grigg-Schellerup in 1992, making it the first spacecraft to visit two comets. The legacy of Giotto, therefore, is one of transformation. It transformed a point of light into a geological world. It transformed a chemical theory into a measured reality. And it transformed our relationship with these ancient visitors from one of passive wonder to one of active, intimate exploration. Every subsequent mission to a comet has been built upon the foundation of knowledge that this small, brave probe provided. It was a quiet, robotic emissary that, in a few short moments, opened up an entirely new chapter in our patient quest to understand the story of our solar system. Beyond its visual spectacle and its rich history, Halley's Comet holds a deeper significance. It is a messenger, a pristine sample of the primordial material from which our solar system was formed. And the most important part of that message, the most fundamental ingredient it carries, is water. The nucleus of the comet is composed of roughly 80% water ice, a vast, frozen reservoir of one of the most essential molecules for life as we know it. This is not water like the water in our oceans or rivers. This is ancient water. It is water that was formed in the interstellar medium even before our sun was born. It was part of the great molecular cloud that collapsed to form our solar system. It was present in the protoplanetary disk, where it froze into tiny ice grains beyond the frost line. And it was this ice that clumped together to form the planetesimals that would eventually become the cores of the giant planets and the trillions of cometary nuclei in the quiescent Oort cloud. The water locked inside Halley's Comet has been preserved in a deep freeze, in a near-perfect vacuum, for 4.5 billion years. It is a direct, unspoiled sample of the water that was available at the dawn of our solar system. The study of this ancient water is crucial for understanding our own origins. One of the great gentle questions in planetary science is where the Earth's water came from. When the Earth formed in the hot, inner part of the solar system, it was likely too warm for water to have been a major component of its initial building blocks. The prevailing theory is that Earth's water was delivered later by a bombardment of water-rich asteroids and comets from the outer solar system. Comets like Halley were once thought to be the primary source of this water. They are, after all, giant balls of water ice. The Giotto mission and subsequent observations have allowed us to study the chemical properties of this cometary water in detail. Specifically, scientists can measure the ratio of different types of hydrogen in the water. There is normal hydrogen, and then there is a heavier version, an isotope called deuterium. The ratio of deuterium to normal hydrogen, the DH ratio, acts as a chemical fingerprint. By comparing the DH ratio in a comet's water to the DH ratio in Earth's oceans, we can see if they are a match. This has led to one of the most fascinating and subtle discoveries about comets. The water in Halley's Comet, and in many other comets from the Oort cloud, has a DH ratio that is significantly different from the water in our oceans. This suggests that while comets certainly contributed to Earth's water budget, they were likely not the main source. The primary delivery may have come from a different class of objects, perhaps asteroids from the outer asteroid belt. But the story is still unfolding. The water in Halley's Comet remains a crucial piece of the puzzle, a capsule of ancient water that carries the chemical secrets of our solar system's very beginning. While water is the most abundant molecule in Halley's Comet, it is by no means the only one. The Giotto mission and other studies revealed that the comet's nucleus is also rich in a diverse array of carbon-based organic molecules. These are not signs of life itself, but they are the fundamental building blocks from which life is constructed. The discovery of these molecules in such a pristine, ancient object has profound implications for our understanding of how life might have begun on a young, barren Earth. The dust that erupted from the comet's nucleus was found to be composed of what scientists call Chon particles, a name derived from the chemical symbols for the primary elements they contain: carbon, hydrogen, oxygen, and nitrogen. These are the four most important elements for life on Earth. When analyzed more closely, these particles were found to contain a complex mixture of organic compounds, including molecules like formaldehyde, hydrogen cyanide, and various hydrocarbons. These are simple organic molecules, but they are the precursors, the starting materials, for building much more complex and biologically important molecules, such as amino acids, which are the building blocks of proteins, and nucleobases, which are the building blocks of DNA. The presence of these molecules in a comet is incredibly significant because it tells us that the chemical precursors for life were not unique to the early Earth. They were widespread throughout the primordial solar nebula. They were formed in the cold, dark environment of the outer solar system and were incorporated into the icy bodies that formed there. Comets, therefore, are like cosmic delivery trucks, carrying these essential, pre-packaged organic ingredients throughout the solar system. This leads to a beautiful and gentle hypothesis about our own origins. In the early days of the solar system, during a period known as the Late Heavy Bombardment, the Earth was subjected to a constant rain of comets and asteroids. Each comet that struck the young Earth would have delivered not only its water but also its rich inventory of organic molecules. Over millions of years, this constant influx could have created a nutrient-rich primordial soup in the early oceans, a chemical environment ripe for the next mysterious step, the origin of life itself. The comet does not provide the answer to how life began, but it provides a crucial part of the context. It shows us that the universe is, in a way, biased toward the chemistry of life. The fundamental building blocks are not rare or difficult to make. They are common, and they are stored in these ancient, icy reservoirs. Halley's comet, as a primordial messenger, carries this profound and hopeful message. It tells us that the ingredients for our own existence were not forged in a special or unique place, but were delivered to our doorstep from the cold, dark, and ancient frontiers of our own solar system. In its dark, dusty heart, we find a direct connection to the chemical beginnings of our own story, a reminder that we are, in the most literal sense, made of stardust. The story of the water in Halley's comet holds a beautiful scientific subtlety, a gentle twist that adds depth and richness to our understanding. As we have learned, one of the most powerful tools for tracing the origin of water is its isotopic signature, the specific ratio of heavy hydrogen, or deuterium, to normal hydrogen. When scientists first analyzed the water in Halley's comet, they were looking for a match to the water in Earth's oceans, hoping to confirm that comets were the primary delivery mechanism for our planet's life-giving seas. The initial results seemed promising. The first measurements suggested that the deuterium to hydrogen, or DH ratio in Halley's water, was similar to that of Earth's oceans. This was an exciting moment, a hint that we had found the source. However, as our measurement techniques improved, and as we studied more comets, a more complex picture began to emerge. More precise analyses of Halley's water, and the water from many other comets originating from the Oort cloud, revealed a DH ratio that was actually about twice as high as that of Earth's oceans. This meant that the water in these comets was a different flavor, a different kind of water than the water that fills our seas. If Earth's oceans were made entirely from melted comets like Halley, they would have a much higher concentration of heavy water than they do. This was a quiet but significant discovery. It suggested that our simple, elegant theory that comets brought Earth its water was incomplete. The story was more nuanced, more intricate than we had first imagined. This does not mean that comets played no role. They almost certainly contributed some water to the early Earth, along with their precious cargo of organic molecules. But they were likely not the main source. The current scientific thinking is that the bulk of Earth's water was delivered by a different class of objects, likely water-rich asteroids from the outer part of the main asteroid belt, between Mars and Jupiter. These asteroids have been shown to have a DH ratio that is a much closer match to our own planet's water. This discovery is a beautiful example of the scientific process. It is a journey of refining our understanding, of letting the evidence guide us to a more complete and accurate story. The initial idea was simple and appealing, but nature, as it so often is, turned out to be more complex and more interesting. Halley's comet, by presenting us with its different kind of water, did not give us the simple answer we were looking for. Instead, It gave us a deeper question, and it pointed us in a new direction, helping us to build a more robust and multifaceted picture of how our own world came to be. It remains a crucial witness, a messenger whose testimony, even when it complicates the story, brings us closer to the truth. When we bring together all that we have learned about the composition of Halley's Comet, its ancient water, its rich organic molecules, its subtle isotopic signatures, a single powerful metaphor emerges. The comet is a window. It is a clear, pristine pane of glass through which we can look back in time, all the way to the very birth of our solar system. It is a direct, physical link to the conditions that existed before the planets were fully formed, before our own world had even cooled from its violent creation. The reason the comet serves as such a perfect window is because of where it has spent almost its entire life. Born in the cold region of the giant planets, it was quickly exiled to the deep freeze of the Oort cloud. In that realm of profound stillness and near absolute zero temperatures, it has been perfectly preserved. While the inner solar system was a place of dramatic change, planets differentiating, volcanoes erupting, atmospheres forming, and life emerging, the Oort cloud remained a static, unchanging museum. The materials within the comet's nucleus have not been processed by heat, pressure, or geology. They are the raw, primordial ingredients of the solar nebula in their original, uncooked state. So, when we use our instruments to analyze the gas and dust in the comet's coma, we are, in essence, reaching through this window and taking a sample of the past. We are studying a piece of the great molecular cloud that existed 4.5 billion years ago. We can see the relative abundances of different elements and molecules, which tells us about the chemistry of the early solar system. We find that the comet's composition of light elements, like carbon and oxygen, is very similar to that of our own sun, which confirms that they were born from the same parent cloud. This window also allows us to test our theories about how planets form. Our models of planet formation predict what the chemical and physical conditions should have been like at different distances from the young sun. A comet like Halley is a direct test of those predictions. Its composition is a data point, a piece of ground truth from the outer solar system that we can use to check and refine our models. It helps us to understand the story of not just our own solar system, but of the countless other solar systems we are now discovering around other stars. Looking through this window is a humbling and awe-inspiring experience. It connects us to our deepest origins. The dust and ice of Halley's Comet are the very same dust and ice from which our planet, our bodies, and everything we know was built. The comet is a primordial messenger, and its message is a chemical recipe, the original instructions for how to build a solar system. It is a quiet, beautiful, and incredibly precious window to a time long before our own. Our journey with Halley's Comet has taken us to the edge of the solar system and back, from ancient history to modern space exploration. We have learned a tremendous amount about this celestial visitor. We know where it came from, we know what it is made of, and we know the story of its long and graceful life. And yet, for all that we have discovered, the comet still holds its gentle mysteries. Each new answer has led to deeper and more subtle questions, and our exploration leaves us not with a sense of finality, but with a feeling of calm and patient curiosity. One of the great remaining questions is about the nucleus itself. The Giotto mission gave us our first, fleeting glimpse of its dark, irregular surface, but what lies beneath? We believe it is a porous, fragile structure, a loose agglomeration of ice and dust, but we have never seen its interior. What is the nature of its structure? Is it layered like an onion, with different materials at different depths? Or is it a more uniform mixture? Future missions to other comets, perhaps one day even a mission that could land on and drill into a nucleus, will be needed to answer these quiet questions. We are also still piecing together the full story of the organic molecules found in comets. We know they are there, the building blocks of life, but we have only just begun to catalogue their full diversity and complexity. Did comets deliver only the simplest precursors to Earth? Or did they also carry more complex molecules, like amino acids themselves? And how did these molecules survive the fiery impact of a collision with a planet? The journey from a cometary nucleus to the primordial soup of early Earth is a path still shrouded in a gentle mist of uncertainty. The precise dynamics of the Oort cloud also remain a beautiful and complex area of study. Our understanding of it is still largely theoretical, based on the silent testimony of the comets it sends our way. How many objects does it truly contain? What is the exact nature of its inner structure, the Hills cloud? And how precisely do the gravitational nudges from passing stars and the galactic tide work to send these messengers on their way? The Oort cloud is the last great unexplored territory of our solar system, and its full story is still waiting to be told. These unanswered questions are not a sign of failure, but a sign of a healthy and vibrant science. They are the gentle frontiers of our knowledge, the places where our curiosity can still wander and wonder. Halley's Comet, on each of its returns, offers us another chance to learn a little more, to refine our understanding, and to ask better questions. It is a patient teacher, and we are its patient students. The beauty of the cosmos lies not just in what we know, but in the vast, peaceful ocean of what we have yet to discover. The story of Halley's Comet is not just one of the past. It is also a story of the future. The comet's predictable, rhythmic journey means that we know, with great certainty, when it will return to our skies. We have a future appointment with this celestial visitor. The next perihelion passage, the next time it will grace the inner solar system, is scheduled for the summer of the year 2061. This future appointment is a source of calm and reassuring anticipation. In a world that often feels uncertain and unpredictable, the clockwork of the cosmos provides a sense of stability. The laws of gravity that govern the comet's orbit are unwavering. Barring any unforeseen and dramatic gravitational encounters, the comet will arrive on schedule. It is currently on its long journey back inward. In December of 2023, it reached its aphelion, its most distant point from the Sun, and began the slow, 38-year fall that will bring it back to us. For many who are listening tonight, the return of 2061 will be an event within their lifetime. Children who saw it as a faint, unimpressive object in 1986 may have the chance to see it again as senior citizens, a bookend to a long and full life. Young adults and children of today have a beautiful and tangible celestial event to look forward to, a chance to see with their own eyes the object that has so captivated humanity for millennia. The viewing conditions for the 2061 return are predicted to be much more favorable than they were in 1986. During its last appearance, the comet and the Earth were on opposite sides of the Sun at the time of the comet's greatest brightness, making it a difficult and somewhat disappointing sight for many casual observers. In 2061, however, the geometry will be much better. The Earth and the comet will be on the same side of the Sun, which means the comet will be closer to us and will appear significantly brighter in our sky. It is expected to be a truly beautiful sight, easily visible to the naked eye. A brilliant reminder of the majesty of the solar system. This future appointment connects us to the flow of time. It gives us a marker in the future, a celestial event to anticipate and to share with the next generation. It is a quiet promise from the universe, a guarantee that the great, silent rhythms of the cosmos will continue, just as they always have. The knowledge that Halley's Comet is out there, right now, falling back toward us, is a comforting and peaceful thought, a reminder that we are part of a grand and ongoing story. When Halley's Comet returns to our skies in 2061, it will be a spectacular sight, brighter and better placed for viewing than it was in 1986. And yet, in a very real physical sense, the comet that returns will be a slightly diminished version of the one that visited us last. It will be a little smaller, a little less massive, a fainter and, in a metaphorical sense, a wiser comet. This is a natural consequence of its life cycle, a gentle and inevitable part of its long story of transformation. As we have learned, every close pass by the Sun takes a toll on the comet. The process of sublimation, which creates the beautiful coma and tails, is a process of erosion. The comet sacrifices a small piece of itself to put on its brilliant display. During its 1986 passage, it is estimated that Halley's Comet lost many billions of kilograms of its mass in the form of gas and dust. This material was cast off into space, adding to the great meteoroid stream that traces its orbit. The comet that is currently falling back toward us is therefore a veteran of another fiery encounter. It carries the scars of its last visit. Its nucleus is a few meters smaller in diameter than it was before. Its surface may have been subtly reshaped, with old jets becoming dormant and new ones perhaps opening up. It is an object that is constantly, slowly, being remade by the very star it orbits. This slow loss of material means that, over very long timescales, the comet's overall activity will decrease. With less ice available to sublimate, it will produce a slightly smaller coma and slightly less brilliant tails with each successive epoch. The change from one apparition to the next is far too small to be noticeable to the casual observer. The comet in 2061 will still be a magnificent object. But if we could compare it to its appearance 1,000 years ago, or 10,000 years ago, we would almost certainly see a difference. It is a fading spectre, but one that is fading on a timescale of millennia, not lifetimes. In this sense, the comet returns to us wiser. It has completed another cycle of its great journey. It has survived another pass through the inner solar system, and has gained another layer of dark, insulating dust on its surface. It has learned, in a physical sense, how to better preserve the precious, volatile ices that lie within its heart. Its slow aging is a process of adaptation, a quiet response to the environment it passes through. When we look up at it in 2061, we will be seeing an object that is not just ancient, but is also a survivor, a celestial pilgrim that has weathered countless journeys through the fire and has returned, once again, to tell its silent story. When we put all of these pieces together, a new and much grander picture of the Sun's family emerges. It is a system of nested structures, each with its own population. There is the small, warm, rocky family of the inner planets. There is the majestic, cold family of the gas and ice giants. There is the sprawling, frozen family of the Kuiper belt. And encompassing them all, there is the vast, ghostly, and ancient family of the Oort cloud. The planets, which seem so dominant from our perspective, are just the innermost and, in some ways, the least numerous members of this great clan. The true population of the solar system is overwhelmingly dominated by its smallest and most distant members, the comets and the icy worlds of the outer darkness. Halley's Comet, in its long, looping journey, acts as a bridge, a traveler that connects these different regions and reminds us of the true, magnificent scale of our home. As we have come to understand the vast and complex structure of the Sun's distant family, we have also come to a clearer understanding of the comets themselves. These beautiful transient visitors are not all the same. They belong to two distinct and separate families, each with its own birthplace, its own characteristics, and its own story. Our exploration of Halley's Comet has been a journey into the heart of this distinction. The first family is the one we discovered in the Kuiper belt. These are the short-period comets, often called the Jupiter family comets. They are born in the flattened, donut-shaped ring of icy bodies that lies just beyond Neptune. Because they originate from this orderly, disc-like structure, their own orbits reflect this origin. They tend to travel in the same direction as the planets, on paths that are not very tilted with respect to the ecliptic plane. Their journeys are confined, for the most part, to the familiar flat plane of the solar system. Their orbital periods are short, typically less than 20 years, as their paths have been shaped and constrained by the powerful gravity of the planet Jupiter. They are the younger, more recently activated members of the cometary world. The second family is the one to which Halley's Comet truly belongs, the family of the Oort cloud. These are the long-period comets. They are born in the vast, spherical shell that surrounds the entire solar system. Because their source is a sphere, they can arrive in the inner solar system from any direction, at any angle. Their orbits can be highly inclined, and many, like Halley, travel on retrograde paths, moving opposite to the flow of the planets. Their orbital periods are immense, ranging from 200 years to many millions of years. They are the ancient ones, the primordial visitors who have journeyed from the very edge of the Sun's influence. Halley's Comet is a beautiful and unique bridge between these two families. Its origins lie in the distant Oort cloud, giving it the wild retrograde orbit of a long-period comet. But a chance encounter with a giant planet has captured it into an orbit of only 76 years, making it behave, in terms of its timing, like a short-period comet. It is the most famous member of a special class of objects, the Halley-type comets, which share this hybrid nature. Understanding these two great families of comets is like understanding the different branches of a great family tree. It allows us to trace their lineage, to understand their history, and to appreciate the different paths they have taken to arrive in our skies. It is a story of two great reservoirs, two celestial nurseries, each one sending its own distinct type of messenger to visit the warm, bright heart of our solar system. Our solar system's distant family is vast, but it is also largely invisible. For every single comet that is nudged from the Oort cloud onto a path that will bring it into our view, there are millions upon millions that remain in their distant, stable orbits, forever unseen. The comets that we witness, the brilliant visitors that grace our night sky, are just the tiniest fraction of the true cometary population. They are the lucky few, the celestial messengers chosen by the gentle chaos of gravity to make the long journey inward. The Oort cloud, with its population of perhaps 1 trillion comets, is a realm of profound and permanent darkness. The vast majority of its residents will never leave. They will continue to circle the sun on their immense, million-year orbits for the entire lifetime of the solar system. They will never feel the warmth of the sun, never grow a coma or a tail, and never be seen by human eyes. They are the silent majority, the great, unseen family of our sun. This thought fosters a sense of immense and peaceful humility. It reminds us that what we can see of the universe is only a tiny sliver of what is actually there. Our sky, which can seem so empty on a dark night, is in fact teeming with a hidden reality. Beyond the visible stars and planets lies this vast, unseen population of our own solar system, a ghostly sphere of sleeping worlds, each one a pristine time capsule from the dawn of creation. The same is true to a lesser extent of the Kuiper belt. While we have discovered thousands of Kuiper belt objects, this is just the tip of the iceberg. There are millions more that are too small and too faint for our current telescopes to detect. They are the unseen wanderers of the solar system's third zone, quietly orbiting in the twilight beyond Neptune. The existence of these unseen wanderers fills the solar system with a sense of quiet potential. It is a vast, untapped library of cosmic history, waiting patiently in the dark. Each new, long-period comet that falls into our view is a new page from that library, a messenger from a realm we can otherwise never touch. It is a gift of insight from the great, unseen majority. This knowledge transforms our view of the night sky. It is not an empty stage with a few bright actors, but a deep and richly populated landscape whose true vastness and whose full family are, and may always be, beyond our direct perception. For all their diversity and their immense separation in space, every member of the sun's great and distant family shares a single profound connection, a shared beginning: the rocky inner planets, the giant gas worlds, the icy dwarf planets of the Kuiper belt, and the trillions of sleeping comets in the Oort cloud are all siblings. They were all born from the same parent cloud of gas and dust, the great solar nebula, that collapsed to form our sun and its planetary system 4.5 billion years ago. This shared beginning is written in their very chemistry. The elements that make up the Earth are the same elements that make up Jupiter, and the same elements that are locked in the ice of Halley's comet. The relative abundances of these elements are a chemical fingerprint, a family signature that unites every object in the solar system. They are all, quite literally, made of the same stuff. The differences between them are not differences of origin, but differences of experience. They are a product of where they grew up. In the warm inner regions of the nebula, only rock and metal could condense, forming the small, dense terrestrial planets. In the cold outer regions, a vast amount of water ice was available, allowing the giant planets to grow to immense sizes, and leaving behind a multitude of smaller, icy leftovers. The comets of the Oort cloud are perhaps the most perfect expression of this shared beginning. As we have learned, they formed in the region of the giant planets, and were then scattered outward to their distant, frozen exile. They are the pristine, unaltered building blocks from which the larger worlds were made. They are a direct sample of the original, well-mixed ingredients of the solar nebula. This concept of a shared beginning fosters a deep sense of connection and unity. It dissolves the artificial boundaries we often draw between different parts of the solar system. The Earth is not a separate, isolated world. It is a piece of a much larger cosmic whole. The water in our oceans has the same ancient origin as the ice in a comet's nucleus. The carbon in our bodies was forged in the same stellar furnaces as the carbon in a comet's dusty crust. To study a comet, therefore, is to study our own family history. It is a form of cosmic genealogy, tracing our lineage back to the great cloud of stardust that was our common ancestor. Halley's Comet, on its long journey from the outermost reaches of the family to its very heart, is a beautiful symbol of this unity. It is a messenger from a distant branch of the family, reminding us of the deep and unbreakable bonds of our shared beginning. Our journey in search of Halley's Comet's home has fundamentally redefined our sense of our own cosmic neighborhood. For most of human history, the edge of the solar system was the orbit of the farthest known planet. First it was Saturn, then Uranus, then Neptune. For a time it was Pluto. Even with the discovery of the Kuiper belt, our sense of the solar system's boundary was at the Kuiper cliff, a distance of about 50 astronomical units from the Sun. But the Oort cloud, the true home of Halley's Comet, reveals the Sun's true and breathtaking reach. The boundary of a star's domain is not defined by the orbit of its last planet, but by the extent of its gravitational influence. It is the line where an object is no longer primarily controlled by the Sun's gravity, but begins to feel the pull of the galaxy and other stars more strongly. This line, for our solar system, is the outer edge of the Oort cloud. At a distance of perhaps 100,000 astronomical units, nearly 2 light-years away, the Sun's true reach is almost 1,000 times greater than the size of its planetary system. This is a profound and humbling shift in perspective. Imagine the planetary solar system, the entire region out to Neptune and the Kuiper belt, as a small, brightly lit room. The Oort cloud is then a vast, dark and silent country that surrounds this room on all sides. We live in a tiny, sheltered harbor at the center of a vast gravitational ocean that belongs to our Sun. The Sun's true reach is not just a measure of distance, it is a measure of its history and its power. The fact that the Sun could fling 1 trillion icy bodies out to this immense distance, and still hold on to them for billions of years, is a testament to the patient and persistent power of its gravity. The Oort cloud is a monument to the chaos of the solar system's youth and the quiet, stable reign of its maturity. This vastness also changes our sense of our place among the stars. At nearly 2 light-years across, our solar system is not a tiny, isolated point of light. It is a colossal structure, a sphere of influence that fills a significant volume of our local interstellar neighborhood. Our nearest stellar neighbor, Proxima Centauri, at just over 4 light-years away, is not a distant stranger but our next-door neighbor. Our Oort cloud may in fact overlap slightly with the Oort cloud of our nearest neighbors, creating the shared frontier between stellar systems. By revealing the existence of the Oort cloud, Halley's Comet and its long-period siblings have given us a new and more accurate map of our home. They have shown us that we are citizens of a much larger and more magnificent empire than we ever imagined. The Sun's true reach is not just a physical boundary, but a conceptual one, expanding our sense of belonging and our appreciation for the quiet, immense, and far-reaching power of the star that gives us life. As our journey of understanding draws toward its gentle close, it is fitting to pause and reflect on the silent force that has been the central character in our entire story. It is the unseen choreographer of the cosmos, the gentle, invisible hand that shapes the paths of comets, builds the architecture of solar systems, and governs the silent, graceful motions of the heavens. This force, of course, is gravity. Our exploration of Halley's Comet has been, in essence, a long and peaceful meditation on the many beautiful and subtle ways that gravity works. We often think of gravity as a simple force that pulls things down, that holds us to the earth. But our journey has shown us that it is so much more. It is a force of creation and a force of order. It is both powerful and incredibly delicate. It can hold a massive planet in a near-perfect circle for billions of years, and it can be perturbed by the whisper of a passing star a light-year away. In the story of Halley's Comet, gravity plays every role. It was gravity that first pulled together the dust and gas of the solar nebula to form the Sun and the planetesimals. It was the chaotic gravitational interactions with the young giant planets that sculpted the early solar system, flinging the icy bodies outward to form the Oort cloud. It is the Sun's persistent, gentle gravity that holds the comet in its vast 76-year elliptical orbit, ensuring its faithful return. Gravity is also the force of transformation. It was a gravitational nudge from a passing star that first broke the stillness of the comet's ancient orbit and began its long fall inward. It was a powerful gravitational encounter with Jupiter that captured the comet into its current, shorter path. And it is the subtle gravitational tugs of the planets that continue to gently alter its orbit with each pass, changing the timing of its return by a few days or weeks. The beauty of the coma and the tails, the very activity of the comet, is an indirect result of gravity. It is gravity that pulls the comet close enough to the Sun for its ices to sublimate. The elegant curved path of the dust tail and the straight radial line of the ion tail are visual representations of the interplay between gravity, sunlight, and the solar wind. The entire spectacle is a gravitational dance. Gravity is the silent, unseen partner, leading the comet through its beautiful looping steps, from the cold, slow waltz of the outer solar system to the fast, fiery tango of its passage around the Sun. To understand the comet is to appreciate the quiet, universal, and elegant choreography of gravity. The very existence of the Oort cloud, the great and distant home of Halley's comet, is a testament to the powerful, chaotic, and ultimately creative role of gravity in the early solar system. This vast, spherical structure was not born in the quiet periphery. It was forged in the violent heart of the planetary region and shaped by the gravitational influence of its largest and most powerful members. In the first few 100 million years after the Sun's birth, the outer solar system was a much more crowded and chaotic place than it is today. The giant planets Jupiter, Saturn, Uranus, and Neptune had not yet settled into their current, stable, and nearly circular orbits. They were migrating, moving inward and outward, as they exchanged gravitational energy and momentum with the vast disk of icy planetesimals that surrounded them. This period of planetary migration was a time of immense gravitational upheaval. The giant planets, and Jupiter in particular, acted as colossal cosmic sculptors. Their gravity was so powerful that it completely dominated the dynamics of the smaller, icy bodies. As these planetesimals, the leftovers from the planet's formation, passed near one of the giants, their fates were sealed in a gravitational instant. Many were pulled inward, either to be consumed by the giant planets themselves, or to be flung into the inner solar system in a great bombardment that scarred the surfaces of the Moon and the rocky planets. Many others were given such a powerful gravitational kick that they were ejected from the solar system entirely, becoming lonely interstellar wanderers. But a huge number of them experienced a third fate. They were flung outward, not with enough speed to escape the Sun completely, but onto vast, extremely elongated and unstable orbits that took them tens of thousands of astronomical units away. This process created a huge, messy, and scattered disk of icy debris. This is where a different, more subtle form of gravity took over. Over hundreds of millions of years, the gentle but persistent tidal forces from the Milky Way galaxy and the occasional gravitational nudges from passing stars began to stir this scattered disk. These external forces acted to lift the orbits of the icy bodies out of the flat plane of the solar system. They randomized their inclinations, pushing some up and pulling others down, until the messy disk was transformed into a vast, stable, and roughly spherical shell. Gravity, in its many forms, was both the violent force that created the scattered debris and the patient, gentle force that sculpted it into the serene and orderly structure of the Oort cloud that we theorize today. It is a beautiful example of how gravity can create order out of chaos. The story of gravity in the life of Halley's comet does not end with the nudge that sent it on its first journey inward. The planets, particularly the giant ones, continue to play a crucial and ongoing role in shaping its destiny. Their gravitational pull is the reason that Halley is the comet we know today, a regular 76-year visitor rather than an anonymous, long-period comet that might visit only once in a million years. When a comet falls in from the Oort cloud, its orbit is a vast, open-ended parabola or an extremely stretched-out ellipse. If it were only influenced by the Sun, it would swing around once and then head back out to the Oort cloud. not to return for an immense amount of time. But to get to the Sun, it must first run the gravitational gauntlet of the giant planets. Each time the comet passes through the outer solar system, it feels the gravitational pull of Jupiter, Saturn, Uranus, and Neptune. Each of these encounters is a small gravitational conversation that can subtly alter the comet's energy and its path. For most long-period comets, these nudges are minor, and they are sent back out to the Oort cloud, their orbits only slightly changed. But every now and then, a comet's path brings it particularly close to one of these giants. In the case of Halley's comet, it was most likely a close encounter with Jupiter that sealed its fate. As the comet passed by the colossal planet, Jupiter's immense gravity tugged on it, acting as a brake. This gravitational interaction robbed the comet of a significant amount of its orbital energy. It was like a satellite using a planet for a gravitational assist, but in reverse. With a large fraction of its energy removed, the comet could no longer climb all the way back out to its distant home in the Oort cloud. It had been captured. Its aphelion, its farthest point from the Sun, was dramatically reduced from tens of thousands of astronomical units to a mere 35. It was forced into a new, much smaller and much shorter elliptical orbit, the 76-year loop that it has been following ever since. The pull of the planets, therefore, is the reason we have a relationship with this comet. It is the force that tamed a wild visitor from the edge of the solar system and made it a familiar, if infrequent, neighbor. And the planets continue to gently nudge its orbit with every pass, ensuring that its path is not fixed for eternity, but is constantly, subtly, evolving in the ongoing gravitational dance. The orbit of Halley's comet, for all its predictability on a human timescale, is not a fixed and eternal roadway in the sky. It is a delicate, evolving path, constantly being reshaped by the subtle and complex gravitational interplay of the entire solar system. The 76-year period is just an average, a snapshot of its current state. The comet's journey is a living, breathing thing, a dynamic trajectory that changes in small but meaningful ways with every single trip around the Sun. The primary agents of this change are the giant planets. Every time Halley's comet passes through the outer solar system, the gravitational pull of Jupiter, Saturn, Uranus, and Neptune tugs on it. These are not dramatic, orbit-altering encounters like the one that first captured it. They are gentle, distant perturbations, but their cumulative effect over many orbits is significant. If the comet happens to pass Jupiter when Jupiter is on the same side of the Sun, the planet's gravity might give it a slight boost, adding a little energy to its orbit and slightly lengthening its period. If it passes when Jupiter is on the opposite side of the Sun, the planet's pull might act as a slight brake, removing a tiny bit of energy and shortening its period. This is why the comet's orbital period has varied over the centuries, from a low of about 74 years to a high of over 79 years. The careful, patient work of astronomers is to calculate these subtle planetary perturbations in order to predict the exact timing of the comet's next return. But the planets are not the only source of change. The comet itself contributes to the evolution of its own path through a process known as non-gravitational forces. As the comet's nucleus heats up near the Sun, the powerful jets of gas that erupt from its surface act like small rocket engines. Because these jets are not perfectly uniform, and because the nucleus is rotating, they can give the comet a gentle, unpredictable push. This push is very small, but over the course of its journey, it can be enough to alter its arrival time at perihelion by a few days. Accounting for these non-gravitational forces is one of the great challenges in predicting a comet's exact path. This delicate, evolving path is a beautiful reminder that the solar system is not a perfect, sterile clockwork. It is a living, dynamic system, full of subtle and complex interactions. The comet's journey is not a solo performance, but an ensemble piece, a dance in which the Sun is the primary partner. But all the planets are also participants, each one contributing its own small, graceful step to the overall choreography. The path is a story that is constantly being rewritten, a testament to the quiet, patient, and ever-changing nature of the gravitational dance. As we conclude our long meditation on the force of gravity, we are left with a final, peaceful impression, one of harmony. The universe, through the gentle and unwavering hand of gravity, is a place of profound and elegant order. The complex and sometimes chaotic journey of Halley's Comet, from its violent birth in the early solar system to its capture and its slow decay, is not a random sequence of events. It is a story that unfolds according to a single, simple, and universal set of rules. And in that underlying order, there is a deep and reassuring harmony. This is the harmony of Kepler's laws, which describe the elegant elliptical paths of the planets and the comet. It is the harmony of Newton's universal law of gravitation, which reveals the single, unifying principle behind all celestial motion. It is the harmony that allows us to predict, with breathtaking accuracy, the return of a comet decades in the future, a triumphant symphony of mathematics and observation. This harmony is not the harmony of a static, unchanging system. It is a dynamic harmony, a harmony of motion and of change. The comet's evolving path, the slow precession of its orbit, the gentle decay of its nucleus, these are not disruptions to the harmony but are part of it. They are the slow, graceful movements in a cosmic dance that plays out over eons. The solar system is not a fixed sculpture. It is a living, breathing, gravitational ecosystem, and its beauty lies in its constant, slow evolution. To contemplate this gravitational harmony is to find a sense of peace and belonging. It is to recognize that we live in a universe that is comprehensible, a universe that is governed by laws that we can, with patience and with quiet thought, come to understand. The same force that holds our feet to the ground is the force that choreographs the dance of comets. The same principles that govern the fall of an apple are the principles that shape the Oort cloud. There is a deep and beautiful unity in this, a sense that we are not separate from the cosmos, but are an intimate and integral part of its grand, harmonious structure. The journey of Halley's Comet, then, is more than just a scientific story. It is a parable about order and elegance. It is a physical manifestation of the beautiful mathematical music that underpins all of reality. When we look up at the night sky, we are not just seeing points of light, we are seeing the visible notes of this silent cosmic symphony. We are witnessing the harmony of motion, the quiet, reassuring and eternal dance of gravity. Our long, peaceful journey with Halley's Comet now brings us full circle, back from the edge of the solar system to our own quiet place of rest. And in this final chapter, we discover the most intimate and profound connection of all. The story of the comet is not just a story about a distant, icy object. In the deepest and most literal sense, it is also a story about ourselves. The very materials that make up the comet, the ancient water, the dark dust, the complex organic molecules, are the very same materials that make up our planet, our bodies, and every living thing we have ever known. This connection is born in the hearts of ancient, long-dead stars. Every atom in the solar system heavier than hydrogen and helium was forged in the fiery core of a star, or in the explosive death of a supernova. This stardust, rich in elements like carbon, oxygen, nitrogen, and iron, was scattered into space, where it mingled with the primordial hydrogen and helium to form a great, cold, molecular cloud. It was from this cloud, this shared cosmic inheritance, that our solar system was born. The dust grains that we find in Halley's Comet are microscopic pieces of this original stardust, preserved in a near-perfect state for 4.5 billion years. The carbon in the comet's dark crust is the same carbon that forms the backbone of the molecules in our own cells. The oxygen locked in its water ice is the same oxygen that we breathe, and that makes up the bulk of our own bodies. The nitrogen in its frozen ammonia is the same nitrogen that is essential for our DNA. When we say that we are made of stardust, it is not just a poetic phrase, it is a literal, scientific fact. And a comet like Halley is a pristine, tangible piece of that fact. It is a direct link to the great interstellar cloud that was our common ancestor. It is a piece of the cosmic womb from which we were all born. This realization fosters a profound sense of belonging. We are not just living in the universe, we are the universe, in a state of self-awareness. The same ancient atoms that have journeyed for billions of years in the cold, silent heart of a comet have also journeyed through the warm, living tissues of our own bodies. There is no fundamental separation between us and the cosmos. The stardust in our veins and the dust in a comet's tail are one and the same. To study the comet is to study our own deepest, most ancient roots. It is to recognize our own face in the silent, dark mirror of the cosmos. The journey of Halley's comet from the cold outer reaches of the solar system to the warm, life-giving vicinity of the sun is more than just the path of an icy wanderer. It is a beautiful and powerful metaphor for a journey that we have all, in a sense, taken. The story of the comet's journey is an echo of the story of the materials that came together to form our planet and, eventually, to form us. Let us trace this parallel journey. The story of the comet begins with primordial material ice and dust in the cold outer nebula. Our own story begins with similar material rock and metal, but also the water and organics delivered by bodies from that same outer region. The comet is formed by the slow, gentle accretion of these small particles into a larger body. Our planet was formed in the same way, through the gradual coming together of countless planetesimals. The comet then spends eons in a quiet, dormant state in the Oort cloud, its materials preserved and unchanging. The materials of our own world, after their own chaotic formation, also entered a long period of quiet development, with the planet cooling and its surface solidifying, waiting for the right conditions to emerge. Then, for the comet, a gravitational nudge begins a long, slow fall toward the sun, a journey from the cold and the dark into the light and the warmth. For the materials of Earth, a similar journey occurred. The water and organic molecules, which originated in the cold outer solar system aboard comets and asteroids, made their own journey inward, delivered to the surface of our young, barren planet. When the comet arrives in the inner solar system, the sun's energy awakens it, transforming its dormant ices into a vibrant, active display. When the building blocks of life arrived on the young Earth, the sun's energy, along with the planet's own internal heat, provided the spark that allowed for the next, miraculous step. The beginning of biology, the awakening of life. The comet's journey is a physical one, a path through space. Our own journey is a chemical and biological one, a path through time and complexity. But the underlying narrative is the same. It is a story of primordial material born in the cold and the dark, that makes a long journey toward a source of energy, where it is transformed into something beautiful, active, and complex. The comet's path across our night sky is a silent reminder of this shared cosmic narrative. It is an echo of our own ancient journey from stardust to sentient beings. The act of observing Halley's comet, whether with the naked eye, a telescope, or the robotic senses of a spacecraft, can be a profoundly reflective experience. As our journey has revealed, we are not just looking at a foreign object, a celestial other. We are, in a very real sense, looking at a distant mirror. In the ancient ice and dark dust of the comet, we can see a reflection of our own primordial past, a glimpse into the cosmic nursery from which we came. This mirror does not reflect our image as we are today. It reflects a much deeper and more ancient part of our identity. It reflects the chemical heritage that is written in our DNA and in the water of our oceans. When we see the light of the comet, we are seeing sunlight reflected from the very same types of dust grains that once swirled in the protoplanetary disk and came together to form our own world. When our instruments analyze the gases in its coma, we are smelling the faint chemical scent of our own solar system's birth. Looking at this distant mirror is a humbling experience. It reminds us that our own existence is contingent on a long and beautiful series of cosmic events. For us to be here, the great molecular cloud had to collapse, the sun had to ignite, the planets had to form, and bodies like comets had to deliver their precious cargo of water and organic molecules. The comet is a tangible link in this long, unbroken chain of creation. It is a silent witness to the processes that made our own world habitable. This mirror also reflects a sense of potential. The comet is a repository of the raw, prebiotic ingredients for life. It shows us that these materials are not rare, but are a common and natural part of the cosmos. In looking at the comet, we are looking at the potential for life that is scattered throughout our solar system and, by extension, throughout the galaxy. It is a quiet, hopeful reflection, a hint that the universe may be a far more fertile and welcoming place than it might appear. To look at Halley's comet, then, is an act of self-recognition. It is a moment to see ourselves not as isolated beings on a single planet, but as part of a grand, interconnected cosmic story. It is a chance to see our own beginning reflected in the faint, ghostly light of a visitor from the deepest, darkest, and most ancient part of our own home. As we gently gather the many strands of our journey tonight, we find that they all weave together to form a single, unbroken thread. This thread connects the very beginning of our solar system to the present moment, linking the vast, cold emptiness of the Oort cloud to the quiet warmth of our own existence. Halley's comet is not just a part of this thread, it is the thread itself, a luminous, tangible connection that runs through the entire story of our cosmic home. The thread begins in the primordial solar nebula, in the cloud of stardust and gas that was our common ancestor. It is here that the comet's material, and our own, was first formed. The thread then weaves through the chaotic dance of the early solar system, a time of planet formation and gravitational scattering, the process that exiled the comet to its distant home and set the stage for the formation of our own world. The thread then stretches out, long and thin, across the vast expanse of the Oort cloud, representing the billions of years the comet spent in a state of quiet, frozen preservation. It is a thread of deep time, a connection to the long, silent middle act of our solar system's life. Then, with a gentle nudge, the thread begins to loop back inward, tracing the comet's long, multi-million-year fall toward the sun, a journey that would eventually make it a visitor to our skies. The thread becomes brighter as it enters the inner solar system, where the comet is captured by the planets and begins its recurring 76-year cycle. It now weaves through the whole of human history, its appearances marking the passage of time and the evolution of our own understanding. It is a thread that connects the astronomers of ancient Babylon to Edmund Halley, and connects Edmund Halley to the scientists who guided the Giotto spacecraft. And finally, the thread reaches us. It manifests as the faint, beautiful light in our night sky. It becomes the streaks of fire in our atmosphere during a meteor shower. It is the data on a computer screen, revealing the chemical secrets of our own origins. It is the quiet sense of wonder we feel as we contemplate our place in the universe. This unbroken thread is a story of connection. It connects the large to the small, the ancient to the modern, the distant to the intimate. The journey of Halley's comet is the story of the solar system in miniature. By following this one beautiful object, we have traced the entire, grand narrative of our own beginning. The thread is a reminder that nothing in the universe is truly isolated. Everything is connected in a vast, intricate, and beautiful tapestry, woven together by the silent, patient hands of gravity and time. Our journey is now complete. We have followed the comet from our own night sky to the very edge of the sun's dominion and back again. We have traced its history, explored its nature, and uncovered its deep connection to our own beginning. And now, we are left where we began, in a state of peaceful contemplation, looking up at the quiet, dark sky. But it is no longer the same sky. It has been filled with a new and deeper sense of wonder, a quiet appreciation for the immense and beautiful stories that are unfolding, silently and patiently all around us. The quiet sky is not an empty sky. We now know that it is a vast, three-dimensional landscape, teeming with a hidden reality. We know that beyond the familiar planets lies the great icy ring of the Kuiper Belt. And we know that surrounding us all is the immense, ghostly sphere of the Oort cloud, a silent family of 1 trillion sleeping comets. The darkness is not an absence of things, but a presence of things that are too distant, too faint, or too patient for our eyes to see. The quiet sky is not a silent sky. It is whispering stories. It tells the story of gravity, the unseen choreographer that guides the planets and the comets in their eternal, graceful dance. It tells the story of our own origins, a story written in the chemical composition of starlight and the pristine ice of a distant visitor. It tells the story of time, of cycles so vast that they make our own lives seem both infinitesimally small and infinitely precious. The wonder of the quiet sky is a gentle wonder. It is not the wonder of loud explosions or startling discoveries. It is the wonder that comes from a deep, peaceful understanding. It is the awe that arises from contemplating the elegance of a law of physics, the patience of a geological process, or the sheer, breathtaking scale of the cosmos. It is the feeling of connection that comes from realizing that the stardust in our veins and the dust in a comet's tail share a common origin. Halley's comet has been our guide on this journey. It has been a luminous thread that has led us through the vast tapestry of our solar system. It has taught us to see the sky not as a ceiling but as an ocean, with depths we are only just beginning to explore. It has shown us that even the most familiar and recurring of visitors can hold the deepest and most profound secrets. So, the next time you find yourself under a dark and quiet sky, allow yourself to feel this gentle wonder. Remember the long, silent journey of the comet. Remember the great, unseen family of the sun. And remember the unbroken thread that connects that distant cosmic story to the quiet, gentle rhythm of your own breath. The sky is not a distant, foreign place. It is the other half of our home. And it is always there, waiting patiently, filled with stories of our own ancient beginnings, waiting to be gently understood. Tonight we have journeyed with a silent visitor, following its path from the brilliant fire of the inner solar system to the deep, quiet cold of its true home. We have learned that this familiar stranger is a primordial messenger, a pristine capsule of time from the very dawn of our own world. In its heart of ancient ice, we find an echo of our own beginning, a beautiful reminder that we are made of the same stardust that wanders the cosmos. And in this shared origin, there is a profound and gentle peace. We are not separate from the great silent universe, but are an intimate part of its unfolding story. The same laws that guide the comet's graceful 76-year dance are the laws that hold our own world together. We are all part of the same harmonious cosmic motion. You can let go of the story now. Allow the words to fade, like the comet's tail receding into the darkness. There is nothing more you need to learn tonight. Simply rest in the quiet wonder of it all, and allow yourself to drift into a deep and peaceful sleep. The universe will continue its silent, beautiful work, and you can simply rest. As you drift peacefully, what celestial wonder fills your dreams? I would love to read your gentle reflections in the comments when you awaken. Thank you for sharing this quiet time with me. If you have found a sense of peace on this journey, please consider liking this narration and subscribing to our channel. It is a quiet way to support the creation of more peaceful journeys for others to enjoy. The cosmos is always here, waiting with a patient and silent embrace. Whenever you are ready for another story, you can find our full library of cosmic explorations to guide you into rest. For now, simply sleep.